for day 2. So yesterday was awesome, so it's going to be difficult to be living up to those standards, but I'll try to do my best today. Couple of things before we get started. So we got some really interesting questions about whether you could actually still use the Jupyter hubs moving forward, and that's fine, as long as, of course, you're not mining Bitcoins, in the middle of nowhere. That should be appropriate.
It's more than fine. It's part of our plan for this hub, right? You're all participants in the center, so you're all able to keep using the hub at this tier. And if you sort of graduate up to being part of LEAP-sponsored research, there's more resources available in the hub, larger nodes, GPUs, etc. So yeah, that's great. Part of the design.
Yeah. And those are CPU-based at this stage. And we would love to hear, for instance, if you're submitting a proposal, you've been using that for a paper, please let us know. We would love to report that back to the NSF. We are being supported by the National Science Foundation, and they would love to hear those metrics. We really want to be a magnet so that people can actually do their research and we can expand. So showing that there's been some great opportunity for expansion. Anything else?
The only other announcement I wanted to make is that should all have been invited to the Slack channel, and there's a Bootcamp channel in there, and we can use that to share links and just code and stuff like that. So if you check your email, if you haven't already, you should see an invite to join the channel, and you can just stay on there and stay part of the community that way.
Great. Thanks so much, Ryan. Yeah. Any questions before we get started, or we're good? Fine? Okay. And so today we are going to talk mostly about neural networks. So it's going to be pretty simple what we'll be covering today. So vanilla type neural networks. We are going to talk about convolutional neural networks, so including spatial features as well. And then we'll talk about recurrent neural networks. So very much linked to what we've seen and covered yesterday, which we are talking about images, so in space. And then if you remember, we had a few time series, so looking at space and time, right? So typical geospatial type of data. They are a lot more sophisticated techniques, but just to give you a sense of some of those basic flavors, we will have what we call 3 studios, so more like hands-on exercises. So we'll go together into a neural network, and we'll try to see how those are designed, And to make it a little bit more fun, so I created a competition, So it's going to be, so you will have to scan that QR code at the end, and you will have 20 minutes to actually get into your neural network, get the most out of it, and you will see and try to get the best results. You report that back into the form, and then we'll see who won, okay? So that's going to be hopefully fun. Any questions? We can also share the links. So those are typical Google Forms, so we can share the links in Slack, if you want. Questions? Fine?
Is there a prize?
So I don't know. We need to ask if we can get some swags, from.
All the leftover Cheetos.
My son would win. Let me tell you, and my daughter as well. Yeah. Okay. So if not, let's get started. We'll try to get some prize here. I'll ask GA. Okay. So let's get into what a neural network is. So that's going to be pretty high level, but I think that should be the right level or pace that we need, and hopefully that will be. And feel free to stop me anytime if anything is unclear. Questions welcome. We are a small community here, small group, so let's use that. Let's use that to our advantage here. Okay. So what is a neural network? So basically, long story short, is people were trying to mimic the brain. So that's when the whole story started at the time. And they started to try and mimic neurons. That's basically what is at the heart of our brain system. And neurons are being connected by synapses. So we'll talk about that later. And basically, the main point was to activate and transfer some information or some signal. There's basically some sort of action potential. So you need to pass some threshold. So you have some activation, some neurotransmitter in that case. And once you pass a threshold, you will actually transmit the information down the neural network, right? And you can have many, many connections. We'll talk about that in a minute. But a very important concept here is some sort of idea of activation threshold, right? You need to pass some level. You need to have some activation. And so by definition, what it means is it's very nonlinear, right? It's a 0 or a step function, right? It could be more sophisticated. We'll talk about that in a minute for neural networks. But that's kind of the idea. A very nonlinear type of response, right? in the real world, and that's actually very interesting, learning occurs through what we call plasticity. So it's actually not fixed, and that's been kind of, I've been fighting with that with my kids. You know, it takes years to train them, you know, and we don't train them, you know, so it doesn't work actually. But when you think about like a dog, for instance, it tends to be a very shallow neural network. We'll talk about that in a minute. Pretty easy to train, you know, so it's pretty easy to modify that to basically influence that plasticity. When you have something very deep, it takes a while, you know. So think about kids, you know, it takes years to have them, you know, like actually perform a task. The human brains had a lot of neurons, so 10 to the 11s, but a lot more connections, you know. So that's one thing we'll look at later, is that we will see that there's a lot more connections typically than the number of neurons. And the connections will be what we will call the number of degrees of freedom, right? So if you remember a little bit of linear regression, you know, the weights that you have in your linear regressions are going to be your degrees of freedom. In that case, your connections, so we will also have weights and biases. Those will be then the number of degrees of freedom. Okay, and that's basically how it looks like. So you have the synapses, so you have the neurotransmitters here. If you take any drugs, that's what you're disturbing here. And that's basically how you're actually impulsing the signal from one neuron to the other one, and then you have a very complex system, and people are very much studying that. And there's a lot of cross-fertilization now between looking at the human brain, so there's the Human Brain Project, and looking at neural networks and trying to actually make some sense of that and trying to understand how people actually learn, you know. And in fact, there's been some potentially a very recent revolution showing that maybe the way we've been training neural networks is the wrong way. So we'll talk about that in a minute. It's okay, we call that backpropagation. Okay, and just to close here, so the brain structure, so we have different parts of the brains for different functions. We will see that some neural networks are kind of doing the same as well. And again, we have some level of plasticity, so some areas can change, and we can actually use that to our advantage as well in the neural networks, right? We might want to change some parts of the neural network by design, because that could be useful. So for instance, you would want to have some sort of classification task, as we'll discuss in a minute, and that's something you could potentially change. Okay? And at the end of the day, we don't really understand the concept of consciousness or thought at this stage, you know, but there's a lot of people, of course, working on that. And just if we look at the history of that, so the idea of neural network actually even started, I looked back at some papers recently, even back in the 50s, you know, that those were some of the early stages, and then really picked up in the 80s when people really tried to make the connection with the real brain. Started to really pick up in the 90s, actually, when I was in early 2000, when I was a college student. We still had some neural network courses at the time, and then it really decayed in terms of popularity. You know, you had some fellows like Jan LeCun and et cetera that were working on neural networks, but it didn't really pick up. And then there was a revolution. You know, and that revolution came from a couple of things. So the algorithmic really developed very quickly. The hardware infrastructure really developed. So we got the GPUs that Ryan was talking about. So we'll talk about that in a minute. And we had a lot more data. That was the advent of the web. So all of a sudden, we had millions and millions of images, millions of videos, a lot of data to chew on. And all of that combined really led to a revolution, right? And to what we are witnessing now, like such as we were talking about ChatGPT yesterday, which is pretty insane and pretty exciting at the same time. But so things like that, where we are really witnessing a true revolution. Okay, so that's been a relatively recent, if you think about that, it's been basically a decade, you know, where we've really seen a resurgence in the use of neural networks and really the revolution that we are talking about every day, you know, in terms of using AI and machine learning. And that's really, as part of LEAP, what we are trying to harness and harvest as well, right? We are trying to actually leverage that revolution as part of climate modeling and for climate change. Any questions? Feel free again to stop me anytime if you have any. I mean, that's pretty introductory at this stage. Okay, so let's look first at a very basic thing. So typically, and especially for this class, so you could have different things. So you could have what we call unsupervised or supervised type of learning. Unsupervised means that we will not have any type of labeled data. So you could think of that, for instance, you would want to do some sort of dimensional reduction in your data set. So you have a very complex data set. You want to reduce the dimension to a few dimensions. Or you would want to do, say, some clustering, right? You have some pretty heterogeneous data set, and you would want to do some clustering, and you don't have any type of label. You know, you cannot say, for instance, you have an image, You don't have any classification to say, or label to say this is a tree, this is a building, and you want to kind of do that automatically. So we call that unsupervised learning, and we are not going to cover that mostly today. A little bit of that, but not too much, right? The main focus today will be on a supervised task, which means that we will have labels, okay? So it means labels that could be in an image, right? Again, trees, buildings, or roads if you're looking at some image. Or it could be a regression task, right? Which is exactly a supervised exercise where you have labels, you know, so you have points. So on your y-axis, you have points, and you want to fit those points. That's what you've been doing with the linear regression, and we want to regress against that, okay? So that's basically the type of concept that we have. We will have some labels. Typically, we will call them y's, you know, so that, you know, think of that as the y-axis that you had in your linear regression. And we are going to try and regress onto that when we have a regression problem. And then the other type of problem for the supervised learning will be a classification. So is it a cat? Is it a dog? Is it a building? Is it a road? Those things, right? So typically it's going to be, in a sense, some sort of integer, right? So integer value. Okay, makes sense? Okay. Okay, so the basic thing that we will have first is thinking of what is one neuron. Okay, so very simple here. So think exactly as your linear regression. You have some weights, right? You take some inputs, so it's going to be multidimensional in essence. So everything we are going to do is going to be multi-dimension. And we are going to have, in that case, m inputs. So those are different real valued inputs here, x1 to xm. We give them some weights, so similar to a linear regression. So we take the sum of that, so xi times the weight. Okay, so that's basically your linear regression, no bias, so no intercept in that case. And we're going to pass that through a sum. Okay, so at this stage, you should be familiar. That's basically just a linear regression, right? So nothing too complicated. And then the only trick here is going to be that part here, right? And that's similar to what we were discussing before, the synapses that we had earlier, right? Where we have this nonlinear type of response, right? And we can make it whatever, okay? It looks like a sigmoid function because that was kind of what people were using in the early stage. They wanted to have kind of the similar behavior as what people have in the brain, which is this activation 0 or 1, right? So, and typically if you're a mathematician, you want to have things that are continuous, the derivative are kind of nicely defined. So that's why they use those sigmoid functions, right? In fact, what we know now is that they are not ideal. They tend to be a bit too complex. They tend to saturate because they are flat on either side. So people don't use them so much anymore. Okay, but just to make the point that we will have some what we call activation functions. So that's going to be very important. Please remember that for your competition and try to find the best one. And we are going to apply that to the linear regression that we have, right? And then that's going to define the output, which is our best estimate of the regression problem. Make sense? So every time we will have a hat here, it means we have an estimate. So that's going to be our prediction, right? So we will have on the left-hand side the inputs, or sometimes called the features, or sometimes called the predictors. And we are going to have on the right-hand side, we are going to have the output, or sometimes called the predictant or the prediction. Okay, so those are different terms. People use different terminologies, depending especially on the field. But that's basically what we have. We have some inputs here, we have some outputs, and we want to predict that to the best of our ability, right? So nothing too complicated at this stage. And we are going to fine-tune or choose different activation functions. Any questions? Fine? Okay. The one thing you can do, of course, and very much inspired by a linear regression, is add a bias, right? It doesn't necessarily passes through 0, right? There could be a bias in your data, so you need to add a bias. So that's going to be the simplest type of what we call a perceptron, right? The simplest neuron you can have is a bunch of weights from 1 to m. So those are the different connections that we will have here. So the number of degrees of freedom plus 1, which is W naught. That's going to be the bias, right? So we have a number of weights here, 1 to m, and then we add a bias. Okay, so that's all we need to have. And basically, if you remember your linear regression, the advantage is for linear regression, we can actually get those weights, right? Does anyone remember how to get those weights? How do we get that for linear regression? Linear algebra 101. maybe this group, I'm sure, knows linear algebra quite well. Yeah?
X transpose X inverse X transpose Y.
So basically a projection, right? You project, right? That would be another way to say that, right? So you have your Y, right, which will be in a different space. You're working in a subspace here, which is what we call a span of the x's, right? And you project, right? That's a linear projection. And we know that when we have a right angle, that's basically your best estimate because it minimizes the distance, right? And if you think about that, minimizing the distance is minimizing the loss, right? It's minimizing the mistake we're making in terms of the prediction, right? Within the subspace that we have, right? So it's just very simple projection, right? So we have that like that, right? Just a bunch of matrix multiplications. That's going to be more difficult here because it's nonlinear, right? So it might not be as simple as what we had for a linear regression, so we will need to actually project in a different way, right? Okay, so you can actually write that, so getting back to what you had here, X transpose W, that's basically your projection, right? So you're projecting onto the space here for the different weights, onto the subspace, which is basically the span of x1 to xn, and that's a mathematical way of actually writing the exact same thing, right? So we are basically taking the sum of the xi times wy, and it's basically a vector x1 to xm, and we're taking the transpose times the weights here, so just the inner product, basically, okay? Inner product, basically it's a projection, right? So it's the same thing here, okay? So just a way to write that, but the main point being that it's going to be a bunch of matrix multiplications here, so you can use a lot of the linear algebra toolkits that you have in the background, so it's going to be nice, especially on your hardware. Okay, so that's for the right-hand side. Now let's look at the left-hand side, which is the activation function. What we said earlier is we want to have some level of nonlinearity here, and again, to mimic the brain, what we would typically want is you have nothing on the left-hand side, right? So if you're below some threshold, you have no influx or some information upstream. And then you can get to 1, right? You just want that typically to be a unit. And once you pass a threshold, so let's say when you're above 4 here, then you're almost at 100%, right? So that's basically what you would want, like some sort of activation function, kind of the simplest type of activation function you could have, which has some level of nonlinearity, and we could always multiply that by some weights if we wanted to expand the range, that's no big deal, right? So that's if we have more range than 0 to 1 in terms of the y output here, okay? And that's going to be a typical sigmoid function, as I mentioned before. It's like nicely behaved because you can also take the derivative. It tends to be kind of annoying, as we'll discuss a little bit later, so we won't use that so much, right? It can be useful if your data is especially between 0 and 1. That's kind of nice because it automatically puts the data between 0 and 1. But beside that, we won't use that so much, right? But just to emphasize that this was kind of the earlier one that people were using because it kind of makes sense when we compare that to the human brain. So that's this sigmoid function. So that's how we write that. We're going to use TensorFlow and especially Keras. So that's how you actually write that activation function in TensorFlow here. That's the shape that we have here. And at the bottom here is the derivative. Why the derivative? You're going to see that in a few minutes. The derivative is actually extremely, extremely important because it tells you basically how sensitive are you in terms of the response of the output to the inputs, right? So that derivative is crucial. And that's why people kind of moved away from that sigmoid function, is because that derivative is actually going to 0 on the left-hand side and on the right-hand side. So it means that you're very sensitive close to the the boundary or the threshold of the activation function, but you're really losing that information on the side. What this means is that when you're training, and we'll discuss what it means to be training, when you're training a neural network, typically you're losing a lot of the information and you can get stuck in what we call a local minimum. So it doesn't work so well. Those are not ideal. They tend to be quite insensitive and very, very sensitive to the initial condition, and that's why people were struggling so much back in the days when they were using neural networks. Okay, so we won't use them again so much. And you have kind of a very similar flavor to that, which is this tangent, hyperbolic tangents, very similar, but it goes from -1 to 1, same type of derivative, right? It goes very quickly to 0 on the left-hand side and on the right-hand side, meaning that you're losing any type of sensitivity, right? So you cannot really tell whether the output is going to change when you're actually changing the input, so not ideal. The one we are going to use a lot is actually this one, which is so simple in the end, which is this rectified linear unit function. And it's basically very simple, right? It's you go from 0 to the left of 0, so it's flat. And then it's a one-to-one line, okay? So basically, you have no response when you're below 0, and then you just follow one-to-one, right? So it's like a regular regression. And so it's almost the simplest type of nonlinear function you could have, right? It's linear and replicating exactly the input when you're to the right-hand side of 0, and to the left, there's no signal, right? So it's the simplest type of nonlinearity you could get. And the derivative of that is basically, as you would expect, 0 to the left-hand side here. And then on the right-hand side is basically 1, right? That's the slope, right? The slope is just 1. So it's, again, extremely, extremely simple, even for the derivative. The advantage being that you're always sensitive to the input when you're on the right-hand side, right? There's never any loss of information when you're going to the right-hand side. So that's a big advantage. Make sense? So that's what people use in practice, this rectified linear unit. That tends to actually work quite well. People were worried back in the days, especially in 0, because if you look at the math, I mean, the derivative is actually non-defined in 0. In practice, it doesn't matter. Okay, so let's forget about that. I was also very worried when I looked at that the first time, but it actually doesn't matter. So we'll mostly use that. Okay, so let's keep that in mind. Yeah. Exactly, yeah. Exactly. So that was made because we had those vanishing gradients. So we'll talk about that in a minute. But because of this sensitivity, we are losing that sensitivity again on the side. And here you're only losing that sensitivity on the left-hand side. And you can actually do something about the left-hand side. We'll discuss that also a little bit later. OK. So why do you need a nonlinearity? Is because very simply the real world is actually nonlinear, right? So if you look at some sort of very simple clustering here, things are not just along a straight line, right? I mean, you can have contours that are pretty complex, so you need to actually capture all of that complexity, and therefore you need to have things that are nonlinear, right, to actually capture the real world, right? So if you had here on the left-hand side a linear activation function, you could only basically divide that world of those two clusters into the green here being here, and then the red being on the left-hand side. It doesn't work so well, right? In reality, what you will need is something much more sophisticated that tries to go across those different clusters. Okay? So it makes sense that we need some level of nonlinearity, whether that's for some sort of labeling or classification, but also if we think about a regression problem, of course. Okay, so let's look quickly at a couple of examples as to what it means, you know. So let's say now that we have just 2 dimensions here, x1 and x2. We'll give them some weights, 3 and minus 2 here. We'll explain in a minute how we are going to find those weights. And then at the top, you could say, remember, we have this bias, right, W naught. But you could say W naught is like W naught times 1, right? So I can consider that as being another weight, right? So basically, you could say I have 1, x1, x2 to xm, multiplied by a bunch of weights, and I'm going to pass that into my activation function, right? And that's going to give me my answer. So let's look at that. So imagine that you have 1, 3, minus 2. So those are the different weights. So first one being a bias again. So you pass that through your activation function. So you will have 1 plus 3 times x1 minus 2 times x2. And you're going to pass that through your activation function, right? So what is that here? Is that it's basically a line, right, if you remember your linear regression. So we transform this 2D space into a line, and we are going to act with the activation function onto that line. So we basically reduce the dimensionality when we did that, right? So we reduce the dimensionality, and we are going to apply a nonlinear function. Okay, so that's basically how it looks like. The space on which we're actually working is actually this line. And whether we're actually higher or lower than that is going to define, it's basically some sort of threshold. It's a geometric threshold, right, that we applied, right, depending on what we have. So imagine that you have a point here, minus 1 and 2. So you can actually compute that. You have 1 plus 3 times -1, -2 times 2. So that's going to be -6. It goes to the left-hand side of the activation function, so we'll be close to 0, right? In that case, if we have a sigmoid function in particular. Okay, so that's basically the idea, is that it basically is trying to cut the space into two parts, right? What is to the left-hand side of the activation function and what is to the right-hand side of the activation function. So really not more than that. Okay, so what we can do now is we can actually start putting a bunch of neurons together. So again, let's consider that as being a bunch of weights multiplied by the inputs plus, again, this bias. So let's consider that as being an input of value 1. Pass that to a sum, activation function, and we can start stacking neurons together. Okay, and we're going to see what happens. Okay, that's going to be the idea. Okay, so that's the simplest we can have. Just one single neuron. So the neuron is going to be, again, this bias plus the sum. We're going to apply the activation function, and now we're going to stack them together to see what's going to happen. So the first thing we can do is basically what we call a single hidden layer. So typically the wording that we have is we have what we call the input layer here. So that's going to be the input here. We're going to have what we call the hidden layer in between. And then we are going to have the output layer on the right-hand side. So typically if you have one hidden layer, in total you really have 3 layers when you're counting, right? So that hidden layer is going to be basically the number of latent variables that we can adjust to actually best fit the data, right? Those are things that we can change that are going to be in the middle, right? The input layers and the output layers, we're not really changing, right? Because that's what we want to predict. And those are the data sets, or those are the data that we are trying to use. So we are not really changing that so much. Where we have the flexibility is going to be at the core here in terms of the hidden layers, okay? And so we can stack multiple hidden layers. So that's going to be one example here with one hidden layer. And we are going to stack also a bunch of neurons, right? So you're going to see in the notebook we will have, basically we could adjust the number of neurons and the number of hidden layers. What we mean by the number of neurons is basically the width of the neural network. And by the number of hidden layer, what we mean is the depth of the neural network, right? So widths and depths, right? And you could change that to see and basically to adjust the number of degrees of freedom. And the important point here is that you can see those are the connections, right? So remember the synapses that we had before. So here we have 3 inputs here, 4 neurons in that particular example. But look at the number of connections that we have, right? We have a lot of them, right? It's combinatorial, right? So you have the first neuron that passes through all of those 4, plus this one through all of those 4, and then this one through all of those 4 as well, right? And same goes to the output as well, right? So those neurons are connected to all of the outputs as well. So what it means is that when you're starting to add a bunch of hidden layers, you will have a lot and lot of dimensions, right? A lot of connections, right? And it's pretty obvious as well that a lot of them are going to be redundant, right? In some ways, right? Especially when you start getting really deep, you might actually go from the input to the output through many different ways, right? And we'll try to find a mechanism to avoid that, right? There might be a lot of redundancy actually built into your neural network. Okay, so basically what we will have is that we will have a neural network here. So what this is actually just a valued function here, right? So let's call that Zi. So that's going to be the neuron here. So let's say Z3, for instance. It's going to be the same as before, right? So some weights, so some bias here, W0, for that particular case. So let's call that 3, plus some specific weights. So the weights that are connected from the input here to that neuron here. So we have 3 of them. They will have some specific weights, so W1, 2, 3 to that neuron number 3 times the input, right? So we have specific weights here connected from the left-hand side to that particular neuron. And that's true for each of them, right? So now all of a sudden what we did is we just built a matrix here, right, of weights. We have a matrix that depends on the size of the input and the size of the number of neurons in the hidden layer, right? So it's basically 2D, right? 2D because you have one dimension here, another dimension here. And that's going to be true across, right? So we are going to have a matrix here, another matrix here if we have some another hidden layer, et cetera, et cetera, et cetera, right? So you will have a bunch of matrix multiplications at the end of the day. Does that make sense? Okay. And if you remember what we had before, we had an inner product, right? We had xj times wj. So you could do the exact same thing. You could write that as a vector x, transpose, and then you have basically, instead of having just some weights, you will have a matrix, right? So it's exactly the same except that we transform that into a matrix form. Okay, so that's what you will have on the right-hand side. And now the only subtlety here is that we're going to have, again, this is similar to a linear regression, right? This is exactly a linear regression. And on each individual neuron, we are going to add this activation function. Typically, just to make things simple, we always use the same activation function because it will be a nightmare, right? You could change that across, but that's going to be a disaster. So we typically use the exact same activation function on each individual neuron. So once you choose one, so let's say rectified linear unit, use that across, right? Because otherwise it's just intractable, right? You don't know what's going on. Make sense? And then typically at the end, what we do is very standard practice for a linear regression is not to have this nonlinear activation function, but to just have a linear regression. Why? Because we just want to scale the data at the end, right? It could go from, say, -20 to 30, or from some other range, right? But it doesn't always go from 0 to something, right? It's not always positive, right? So that's why we typically just at the end, it's very standard practice, again, to just have a linear function, right? So what we do is we basically remove that activation function at the end, and we just say it's going to be just some bias plus some weights times the last hidden layer. Okay, so to summarize, we'll have a bunch of activation functions at the core of that, so in the hidden layer. And in the last layer, just for the output here, we are not going to use any type of activation function, just a linear regression. It makes life much easier, okay? Just it scales the data. Does that make sense? Or fine? Not losing anyone? Okay, so now a quick thing is, what happens is if I transform G into just a linear function. So remember what we had. We said we have those G's here. But one thing I could do is I could actually transform that into just a linear function, right? And you will see in the notebook that we have at the end, what we did is we transformed that activation function into just linear. So what this means by definition is that we're transforming that G to become basically the identity, right? So there's nothing, right? So you have your linear regression, you go to the next pass, which is after the activation function, and this is just identity, so you can basically get rid of that. So what this means is that it's also very standard practice. You take your neural net, and you have your activation function, and you can always transform that back into a linear regression, right? And it's super easy to do. What you do is you just say, I take my neural net, which was pretty complex, and I just transform my activation function, and I transform that into a linear activation function. And what it will do implicitly is that it will put a bunch of weights here, a bunch of biases, stack them together, and just take the sum of that, and it's just a linear regression, right? So the output is going to be a linear regression of your input, okay? But it's a good way to always check whether you're seeing any type of improvement by going into a nonlinear world, right? So instead of just doing your linear regression, you could also project, as we discussed before, but that's an easy way to check. You know, you could actually have your linear regression. So that's very standard practice. You take your neural net, and then you just change your activation function into a linear one. Make sense? Any questions so far? Shouldn't be too, yeah? All right.
Maybe just difference in the language that we use in social science. Can you go back to the image with the inputs, latent, and the, yeah. So can you explain again what's the difference between the latent structure you're going to identify and the output?
So the output is what we want to predict, right? So those could be a classification problem. We want to predict like roads and buildings and trees, you know, on an image. Or it could be a regression. We want to predict, say, the temperature in New York in 2080, which is what we are going to do later. So that's the task, right? That's what we want to predict. the input is going to be, in our particular case, it's going to be the concentration of carbon dioxide. And then I will have a bunch of things, and frankly, I have no idea what it is. But we are going to learn that, and that's why people sometimes don't like neural nets. They say that it's a black box because we have no idea what those neurons are. In fact, you could actually check into that and get into the gut. We call that trying to get into explainable AI, trying to get into the gut of your neural net and why you got that prediction, for what reasons. But typically, we don't know. We will have just a bunch of values that are changing as a function of the inputs, right? Remember that here, those are dependent on the inputs, right? So they are going to vary as we vary the CO2 concentration or the methane concentration here. And we are going to have different, basically, prediction for the temperature in New York as a function of the time or as a function of the concentration. And that's because those values are going to change, right? They are changing because they have weights that are being applied, but also because we are passing sometimes those activation functions as well. So things can be quite nonlinear as well. Does that make sense? But typically, we don't know what those are. So they are just a bunch of, and what will, so those values, we typically very rarely actually look at the values here. But what we'll try to focus on are going to be the weights here. Okay, that's going to be the primary thing we'll be focusing on today, is getting those weights. So the weights are not going to change, right? So the weights here, they are fixed, right? Once we've trained the neural net, they are going to be fixed. What's going to change, to get back to your point, is going to be the inputs, right? Different types of images, different types of CO2 concentration. So that's going to be the thing that changes, right? And maybe that's one thing that's typically a bit unusual when we think about neural networks, is that typically we want to fit some regression as a function of the input, right? Here, what we are trying to really fit are the weights, right? Similar to a linear regression, right? We are trying to find the right weights or the right angle, right? And that's really at the core of the neural network, right? The input sensitivity, we don't care so much, right? And that's why people never really, I mean, not directly look at the input, the sensitivity of the output to the input, right? They really care about the sensitivity to the weights. Does that make sense? Yeah?
Following question about if we increase the number of neural or the number of the hidden layers, we will get better results?
We are going to see that, yeah. So long story short, you know, so there's actually a theorem that tells you that if you have pretty much an infinite number of neurons, even with one hidden layer, you can basically mimic or replicate any type of function, you know, even the most complicated function, you know, so that you can actually show in the limit you can reach that. And so that's why in the early stage, especially in the 80s and 90s, people invested a lot of time in like expanding the width of the neural network. It's going to be very clear when we are going to look at images, you know, that this is the wrong thing to do, actually. It tends to lead to very overfitted neural nets, and the best approach is to actually increase the depth of the neural network. And why is that? It's because every time you go through another hidden layer, you actually increase kind of the degree of abstraction, you know. So you can think of that like, it's very clear in the image, you know, you get from like some diagonals or some crosses or, you know, some squares. You bring them together, it becomes like an ear, a nose, you know, and then you bring them together, it's a face, you know, and then you can change like a bunch of faces, you know. But it's very clear that you have a degree and level of abstraction that builds in across the different layers, you know. And you become more and more abstract, you know, very, very low level on the left-hand side and very, very high level on the right-hand side. And so that's why people now prefer having, you know, so that's why that was kind of the revolution of deep learning, right? Actually having very deep neural networks. I mean, there's nothing sophisticated about deep learning. It's just a neural net that's deep, and what is deep, you know, everyone has different, how can I say, criteria for that. So I'm not a big fan of deep learning as a word, but anyways. The main point being that it means that there's some degree of abstraction that is built in. Any other questions? Fine? Okay. Okay, so basically then the idea is that you can extend that, right? There's nothing that prevents you from getting back to your point. So you have again, this hidden layer here, and we can basically stack a bunch of them, right? It's as easy as it gets, you know. And so the way it's going to be done in Keras, we are going to see that later, is we are going to call that a dense layer. Why? Because it means we are connecting every neuron on the left-hand side to every neuron on the right-hand side, right? So there's a connection here going from that particular neuron to all the neurons in the later hidden layer, right? So that's what we mean by dense, right? We are connecting everything from the layer ahead to the layer after that, right? Make sense? So dense is something we should remember. We are going to use that, okay? And in fact, in Keras, you're going to see it's very simple. We are going to define that as a model. We are going to just add layers, and we are going to say that's going to be a dense layer, and it's going to take as input the previous layer, and the output is going to be the next layer, right? So it's going to be really, really easy to build, right? It's almost like geometric, you know, you will see. And you can stack a bunch of them, right? So now you could have as many hidden layers as you want, right? I mean, nothing prevents you from doing that, you know? And again, you will actually have higher and higher levels of abstraction as you get to the right-hand side. Now, of course, I mean, it's a trade-off, right? I mean, it depends on the size of your data set. Like, think of that like every connection here is basically one weight, right? Plus the bias, but let's mostly focus on the weight. It's basically 1 degree of freedom, right? So remember your linear algebra when you have a linear regression. If you have a data set of dimension 10, you have 10 data points. Not sure you want to get to more than dimension 10, right? Because you cannot really fit those weights, right? So it's a trade-off, right? Like, what is the dimension of the neural net that you're going to use? It also depends on the size of the data set, right? And so that's going to be a lot of the trade-off that we have. We'll also discuss that in a minute, is how can we actually find those weights? And that can be one of the roadblocks that we have. Okay, so that could be also an issue. Okay, and so that's one example I gave in my class, is that, you know, you could have some very simple predictors, like X1 is the number of lectures you attended, the number of hours that you spent on the final project, and then those are that's the data set that you have, right? And so one thing that's actually very important in machine learning is that we are reversing the approach, right? In the sense that, you know, back in the days, people were coding, say, you know, if I pass through that, then do that. You know, those were a bunch of if statements. You know, that's where you know, especially in chess, you know, people say, if the king does that, or if the queen does that, then do that, right? That's how people were actually playing chess, right? Or they were programming video games. What we are doing here is the converse. We are saying, I've seen some data, or I've been exposed to some particular examples of chess or the Go games were revolutions with machine learning, because people never trained the machine to actually play chess, right? There was no code saying, you know, if the king or the queen does that, you do that, right? But instead they said, let's look at some game and let's learn from the game, right? And that's what we are trying to do. We are looking at some data and we want to learn the game, right? We want to learn the code. We want to learn the script, right? So we are reversing the approach, right? We are not imposing the script. We are learning directly from the data. So it's really reverse engineering things, right? And people showed that it's actually way more powerful, because oftentimes you don't know the rules, right? For instance, the Go game is actually very, very complex, right? You cannot code all of the cases. You've never seen that. You will never see that in your life. But you can actually learn from the data, right? So maybe if you've seen a lot of games, and what you can even do is actually have computers play against computers, so you can generate data. But in that case, you're actually being exposed to data, and you want to learn the rules based on just seeing the data. You know, that's what we are doing with machine learning. You're seeing data, you want to learn the code. You want to learn the script based on the data. So in that case, the simplest case, you want to learn the clusters based on the data, right? You have some data, you want to learn the rule, right? And you don't know the rule a priori, okay? So that's basically the data set that we have. This is what we will call our training data, right? So we have some fading here, some students that pass, and we want to basically kind of do some sort of classification here. So let's say that we have a point here, 4, 5. We want to say that this is going to be a pass, right? Because it's within that cluster, right? But how can you do that? That's going to be the question, right? How can you infer that just by seeing the data here is going to be the main question we're trying to address. Okay, so how can we do that? We have this new data point here, 4, 5. So you can think of that, those are two inputs, right? X1 and X2. We pass that through some neural network. The dimension doesn't really matter here. And we are making a prediction. Prediction is very simple here. It's binary, 0 or 1. 0, you failed. 1, you passed the class, right? And what we are trying to do is, like, you could say, I pass that through my neural network. Remember that my neural network has a bunch of weights. Let's assume that they are given to us, right? We don't know anything at this stage, but we have a bunch of weights. We pass that through that. We have some nonlinear activation function. And the prediction we are getting is 0.1, right? It's not that great, right? Because if we look at the clusters nearby, right, we can look and it looks more like a pass, right? So it looks more like a 1, right? So we would want to minimize some sort of distance, right? We want to minimize the loss. We want to be as close as possible to 1, right? So that's going to be the primary thing we want to do here. Okay, so it means that we first need to do one thing, which is to define a loss. That's going to be very important. Same goes for the exercise that we will be doing later. We define a loss, which is some sort of distance between the prediction that we have, so the y hat. That's a complicated way to put it. So it's a function of the input here, of the weights as well. Those are some parameters, right? They are the parameters of the neural net. And we are looking at a distance compared to the actual. I don't want to call that a distance because, you know, if you get into the weeds, sometimes they don't have a property of a distance. But the main point being it's a loss, right? We're trying to measure the discrepancy between the prediction and the actual value, right? And of course, what you would want to do is you would want to minimize that, right? So typically, we want to minimize the loss. We want to actually try and mimic the data set as close as we can, as possible. Make sense? So what can we do in that case, right? So it means that first, the neural network that we had was not great, right? It's a pretty bad model. It's a bad predictive model, right? So what can we do to improve that? Sorry? Oh, you're too fast, yeah. Yeah. So what do we need to do? Exactly. We need to change those weights, right? So it means that think of a regression problem, right? So you have some weights. The weights were not great, right? They were not really the right ones, so we need to adjust those weights. So that's going to be what we will call the training, right? So the training depends importantly on a loss, right? We need to define a loss. That's the objective function we want to minimize. Once we have that, we are going to try and use the weights. The important thing here is that sometimes people are confused in the sense that we are going to be exposed to a bunch of data sets, right? So the x's are going to change, right? So we will have multiple points for the loss, right? So not just one point, but many losses or loss terms. And the one thing we're adjusting are not the inputs, right? The input is given to us. Again, that's part of our data set. We have some labeled data where we have the output and we have the input, right? We know if it's a pass or a fail, and we know how many hours they spent, right? But the only thing we can change is the inner gut of the neural network, right? We can only change the weights here. Make sense? So we are not changing the input and the output, right? So not the x's and the y's, we are just changing the weights. We are tuning the regression, right? We are tuning those slopes, right? And we need to do that in an efficient way, okay? And that's basically one of the revolution of neural net, of machine learning. Make sense, or any questions here? Okay, so basically, another way to frame that is that we have a loss that depends on the weights, right? So that's really what we care about, right? That loss is going to be depending on the weights. And you can call that in many different ways. Like it's an objective function, it's a loss, it's a cost function. Sometimes it's called empirical risk in economics. And basically, we're looking typically at the mismatch, right? So that's a loss. And typically, the mean value of that. So could be squared of the error, and we take the mean of that. Or it could be the absolute error, right? So depending on what you care about. Or it could be the accuracy, you know, depending on what you want to look at, you know, depending on the type of problem. But the main point is that we will have a bunch of labeled data. And this is our initial prediction point 1. That's the truth 1. Here's our second prediction point 8 for another data point, which is 2, 1. And the result here is 0. Then the third one that we have is 5, 8. and then we want to predict 0.6, we want to predict 1, and we got 0.6, right? So let's tune those weights to best match the actual observations here. Make sense? So that's going to be, the goal here is trying to actually reduce the mismatch between the prediction that we have here and the actual one. Okay, so trying to improve the prediction that we have with the neural network. Okay, so in that particular example, no need to get into the weeds, but this is what we call the cross entropy. So when you have a classification task, that's the typical type of loss that you use. And that's coming from information theory, so no need to think too much about that. That's kind of like a probability, log of the probability. So that's what we are trying to minimize. We are trying to minimize the mismatch in terms of how frequently we got those correctly or incorrectly, right? So we have that here. So this is the prediction here. Oh, sorry, that's the actual here. This is the predicted here. So it's like probability, log of probability. And we want to also get the converse, right? Not just the truth, but also what was mistaken, right? So the false classification. So we also do 1 minus the actual, log of 1 minus the prediction, okay? No need to think too much about that, but basically what it means is that when it's binary between 0 and 1, you can think of that as a probability, and we are trying to basically maximize the prediction as much as possible, and you can mimic basically what we define as the entropy in information theory, which is minus the probability or log probability. This is the entropy. So we are trying to minimize the entropy of the system. Okay. No need to get too much into that. Yeah?
So we're trying to fix the weights here. So is this the same steps you would do to generalize? Like if you had another mix of grades?
Yeah, so the prediction is going to change as a function of the weights. And same here, right? So that's for the actual prediction and the mismatch here. So we are trying to improve the accuracy in that case. And what we are trying to do is we are trying to minimize that loss by adjusting those weights. Okay, so we are trying to get the best match to the observations using those predictions.
Yeah, so what I'm saying is like, so with this, for another mix of data, is this the same steps you do to generalize for the other?
So that's a great question. So we are gonna talk about that a little bit later, but so that loss is, you're right, on that particular data set. And typically what we will do is we will take the entire data set, we will split that into some fraction which will be called training data, typically 80% or 70%, and then the rest which will be called validation. And we'll use that to make sure we are not overdoing the job, right? Because it will be super easy to go through every single point, right? But then you might, and we'll talk about that later, but you might be overfitting. And so that validation test set is going to be used to check that we are not overfitting too much. Yeah, that's a great point. But you're right, we'll assume that we are computing that loss on some fraction of the entire data set, which will be called the training data. Just to conclude very quickly, so in the end, it's very easy to do actually in TensorFlow, right? So there's no need to compute this very complex loss. If you have a classification problem, you're going to use this softmax cross entropy. So that's what I meant, is that when you have a classification task, we are going to use that type of loss. So we want to make sure we are getting the classes right. And we are going to get just the mean of that, right? The average across the entire data set. So that's the way you write that. Okay, so that's going to be your loss between the model Y and the model prediction. So model Y is actually the labeled data, and model prediction is the prediction, right? So that's basically the loss we are trying to minimize here, the average cross entropy between the actual labeled data and the prediction, right? The mismatch. And when it's a regression, we are going to replace that by the mean squared error, typically, right? What is basically the difference that we have along the y-axis, okay? So that's going to be pretty simple. Okay, so for a regression problem, that's going to be that. You have the actual value here, you have the prediction there, so that's your y hat, if you will, which is on the right-hand side here. And in that case, it can take any type of values, right? Any type of real valued characteristics here. So that could be, for instance, the final grade that we are trying to predict. So we are trying to be a bit more granular. The prediction here is 30 instead of 90, 80 instead of 20, 85 instead of 95, and we want to optimize that, right? We want to minimize the distance here. And the typical one we are going to use is going to be the mean squared error. So the distance here, so this is the error, and we don't care whether it's a negative or a positive value, right? So that's why we take the square of that. And we take just the average, right? We just want to take the average mistake, right? And so that's basically how we're going to do that. So that's going to be the mean of the mean squared error. In fact, there's even an easier way to write that. So that's the mean squared error between, again, the prediction and the model, the model label data. Okay. So that's what we are trying to minimize here for a regression problem. And again, when you have a classification task, that's going to be just that here. Okay, so we are mostly going to focus on those two, and that's going to be the losses we want to minimize here. Make sense? Okay, so now the rest of the class is going to be how we actually get those weights right? So the prediction is bad, and so what we want to do is we want to improve the prediction, right? That's kind of the ultimate objective here. And so you can write that in mathematical terms. What we want is we want to find the best weights, right? And the best set of weights, typically we call that in mathematical forms as W star, which are the weights that are minimizing the loss, however we define our loss. And we typically write that as argmin, right? The weights that are minimizing the loss. That's what we want, right? So first word of caution here is that there's not one single set of W star. Okay, so that's the typical mistake. People say, oh, I have the best neural net. That's wrong. Okay, it doesn't exist. Okay, so typically what you'll find is that you retrain your neural net and you'll get different weights, and they are equally good in terms of the loss. And again, why is that? It's because if you remember, there's a lot of connections, right? And so there's a lot of redundancy. So you can get the same results for many different reasons, right? And so that's why you always need to be careful, because it means that when you want to explain your results, you could actually get the same response for many different reasons, right? So that's the unfortunate truth about neural networks, right? So that's one thing to put in mind, is that it's a beautiful way to write it, but it's wrong in a sense, because there's not a single set of weights that's better than the other ones. And why is that? Is that typically, if you look at that typical shape of a loss function, it's actually a real one here, just in 2 dimensions, right? And you can see it's already pretty complex. And what we want, remember, this is the loss here as a function of those weights on a particular data set here. So that's, to get back to your point, that's on a particular data set, on the training data. That's the shape of your loss. And those are the minimal points, right? So they are almost equally good, right? But the main point is that we are in 2 dimensions only, right? Typically, we will have to deal with millions of degrees of freedom. And so you can imagine the complexity of this loss function, right? And what we will want to do is we'll just want to get to that minimal value here, okay? And we'll see that we have many good minima that can actually minimize this loss. That's going to be the trouble, okay? It's not typically an issue, but it means that the best neural networks are typically non-unique, right? You have many neural networks that are equally good, right? And sometimes you're lucky, and sometimes you're not, right? You run your algorithm, and sometimes you get a great result, so keep it, And sometimes it doesn't work, it just fails, you can never train, and just bad luck, right? So it's part of that, right? Okay, so now what we want to do is that, basically, if you look at that shape, what we want to do is we want to get there, right? This is the minimum, that's basically the point that's minimizing the loss. So we want to get to this weight here and to that weight here, right? And imagine we are starting at the top. Okay, so that's where we are going to get started. So we are starting here. So how do we get down here? And people who know neural networks, please don't answer. So how do you get down? Any idea? So again, what we want to do is we want to minimize the loss. How do you minimize something? That would be derivative 101. Yeah?
According to the gradient.
Exactly. So that's right, yeah. So I'm taking the gradient here, but it goes up, right? So that's the gradient of the weight, right? And it's in 2D, right? We write it this way. So that's the gradient of the loss with respect to the weights, but dw is a vector, so if you've done that, if you've never done that, doesn't really matter, but it's in 2D, right? You take the gradient along W naught and the gradient along W1, and it's in 2D, right? You can do it in n dimensions. But now you're not going to the right direction, right? So what do you do now? Sorry?
Go the other direction.
Yeah, you go the other direction. Sounds simple. But now you're too fast, right? So what do? It's actually written here. So yeah, so basically that gradient typically is too big, right? The error, if you look at that, because we're just at the very top here, but you know, when you get to the bottom here, you know, you need to go kind of slower, right? I mean, it's like descending down a valley. I mean, you can start running, but at the end, you know, you better be careful. You're going to be falling into the river, so you want to decelerate, right? So typically, you want to go down, but you want to go down not so fast, right? Otherwise, you're going to be jumping back and forth, right? So that's typically the thing is that you go to the opposite direction, and you don't go the full way, which is going to be 1. You take a fraction of 1. And that fraction is going to be what we will call, so that's going to be this parameter here. We are going to call that the learning rate. Very important for the competition later, so pay attention to this guy. A learning rate is really important, right? So it's basically how quickly you descend. If you're too fast, you're going to be bouncing back and forth, right? So, sorry, we are going to, if you go too fast, so imagine I take a really big learning rate, so I will be going down, and then I bounce back, I will be bouncing back and forth. If I'm too slow, you know, it takes forever, you know. So when I stop my algorithm, I might stop here, you know, I never manage to actually get down the valley, right? So there's some threshold, right? There's some better value, and it depends on the type of problem you're looking at and the complexity. Yeah? So what it means is that the learning rate is going to be what we will call a hyperparameter. It's something that we need to tweak and tune, and that's something we are going to do in the notebook, and that's going to be affecting the quality of your results. And actually, that's an important comment, is that when people say, oh, I managed to fit this neural net, to me, it means nothing, right? Okay, give me a neural net, it means nothing, right? What is the number of neurons that you used? What is the number of hidden layers that you used? What is the learning rate? Those are what we call the hyperparameters. What is the activation function that you used? Those are the important points. Someone reporting in a paper a neural network and say, oh, I've fitted that neural network to my data. I mean, to me, I would reject the paper. It doesn't mean anything, okay? What is useful is knowing what is the structure of your neural network, what were the hyperparameters. So those hyperparameters, again, the number of neurons, number of hidden layers, the learning rate, even the activation function and the activation function. Those are the things you can change to best fit your data, okay? And those are the things you report in a paper, okay? You can actually automatize that. You can actually find the optimal one. So there are some really nice toolboxes. One is called Optuna, and they try to do the job for you to find those hyperparameters. So the best number of neurons, the best number of hidden layers, best learning rate, et cetera, et cetera. We are not going to use that today. Otherwise, you will be winning, of course, the competition. Yeah?
Here, there's some random sampling involved, right? To get some sort of gradient, you need like some idea of the field. Is there sort of some heuristic to that, how to set that up? Because I imagine you could also get past or get close to some minimum by just random sampling and getting an idea of how noisy or how, I guess, a number of minima.
Yeah, so that was a lot of the issues in the early stage, especially when people had those sigmoid activation functions, right? They could actually, typically things were extremely dependent on where you were starting from the initial condition, right? And that led to a lot of stochasticity. So you had a bunch of papers looking at the impact of initial condition in your network for the training. But a lot of that is gone now, that people use those rectified linear units. They are way more stable. So it means that you'd better be pretty unlucky to not fit correctly your data if you do it the right way in terms of like learning rate, etc. But typically, you will get a fit every single time, a pretty decent one, you know. I mean, sometimes you can be unlucky, you know. I'm sure Weiwei will complain if I say that every time you get a good fit, but most of the time it works, right? Whereas back in the days before, people were running a bunch of them, and that was adding to the cost. Now it doesn't work, so I mean, we don't really have that issue because we are never getting those the vanishing gradients, as we'll discuss in a minute. Okay, but long story short, it's very important to get those hyperparameters right. So number of neurons again, hidden layers, activation function, and learning rate. Okay, so those are at least the 4 that you should pay attention to. Yeah?
What was the name of the package you said is optimizing the whole thing? The example package?
Optuna, O-P-T-U-N-A. There's another one actually from a collaborator at UC Irvine. So I'm blanking on the name now. I'll remember, but that's for PyTorch. Optuna is typically for TensorFlow. Yeah. There's another one also. Yeah, I can send you a bunch. There's like 3 or 4 now that are very typical to actually optimize those. Yeah. Okay, so let's try to just to make sure we have time. So basically, the way it works is you initialize your weight to get back to your point, Julius, right? You initialize your weight. That used to be very important. It's not so important anymore. And then what you do is you start from there. You will have a big mismatch, of course, right? Because it's a completely random neural network, right? So you're off. And now you're trying to reduce your offset, right? Your mismatch. And you do that by first computing your loss, and you compute the gradient to the loss, right? What if you were going in that particular direction along the weights? Will that increase or decrease your weights? And then you multiply that gradient by a learning rate, and you will adjust your weights, okay? So you go down gradient of that function that we saw here. We just multiply the initial weights by some learning rate, and we add that, and we will try to get here, okay? That's just what we do, okay? So in the end, it's actually not that complicated, right? So what we are trying to do is we take a gradient of the loss that depends on the weight, multiply that by a learning rate, add that to the weights, and that will be the update of the weight. We recompute the loss, and we do that again and again and again until we are satisfied, right? And what we mean by being satisfied is we see that the loss basically is plateauing, there's no change, so there's no need to bother continuing the process, right? So we just stop, right? I mean, we can be basically within the noise, or it means that we cannot exactly fit the data with the neural network, so let's just stop, okay? Fine? So what is complicated here? So what's the main trick here? Or what's the main issue now? So we know how to get down, right? So we know we have this algorithm here, so pretty simple in the end. But what is complicated? Sorry? Who said that, sorry? Yeah, that's true. The dimensions are pretty complex. You can have millions of degrees of freedom. So in fact, the weights here are not just 2 dimensions. I showed you 2D, but in fact, typically you have millions of degrees of freedom, right? So what is an issue?
That's why we do mini batch, right?
Yeah, sorry?
Like, do degree on the whole thing, right?
Yeah, but what about that?
Yeah, the diminishing/exploding gradient.
Yeah, but even simpler than that, how do you get that? I mean, it's a gradient, right? But it's complicated, right? I mean, it's a gradient of something. Remember, like, I mean, we have to, I mean, I don't want to be annoying here, but, you know, let's imagine I'm the first neuron. I want to know the dependence at the end here as a function of the weight in the early stage, right? Kind of annoying, right? Right, so we need to have a trick to compute those gradients, right? They are actually complicated, but there's a nice trick, which was just mentioned now, which is to use chains rule, right? So how does it work? We want to minimize that loss. Remember, the loss is just a function of the prediction y hat, right? So can be the mean squared error. Again, this cross entropy doesn't really matter that much. But that y hat will depend on a bunch of weights, right? And what we can do is we can actually do that backward, right? We can say, in fact, my prediction here depends on the last neuron I saw, right? And there was a weight here connecting Z1 to y hat, and it had a weight W2, right? So there's a sensitivity here. And then before that, there was a weight W1 that was affecting that Z1, right? So if I want to know first the sensitivity to W2, right? it's pretty straightforward, right? So I want to know in that particular case, because I need to tweak and tune and get that gradient here, what's the sensitivity of the loss to W2? Okay, so just change rule, right? Very simple because the loss depends directly on the prediction. So this is something we know, right? It's the shape, right, of the loss. Mean squared error, so it's 2 times the absolute value of y minus y hat. So we know that, right? So it's straightforward to find. We can know that actually analytically, right? Straightforward. And then we just need to get the gradient of y hat to W2. Okay? But remember, we're almost like a linear regression, right? Especially if we use a rectified linear unit. If we are to the right of 0, y hat and the sensitivity to W2 are just going to be Z1, right? And then if we are to the left of that, the sensitivity is 0, right? So it's really straightforward to get that. It's just the activation function, right? So this gradient of sensitivity is actually really straightforward, right? So it's just this 0 or 1, right? And then we can actually go forward, right? We could say, let's look at the sensitivity to W1, which is ahead of that. And we can just continue, right? It's going to be the same, dy hat dz1, and then dz1 to w1, right? So I can do the exact same thing. I just split my dy hat to dw1, so the sensitivity of the output to my neuron, to my weight, which is way ahead, right? And I'm going to split that, right? It's like the same as dy hat divided by dz1 and dz1 divided by dy11, right? So I just split in terms of the middle hidden neuron, right? And that's what we have, right? So it's the same as that, right? Remember, I just broke the right-hand side here into those 2 pieces, right? And now that's straightforward, right? It's the same as what we just computed before. We know how to compute that. And now it's the sensitivity. It's the same, right? It's just the activation function that we had before, right? If you're to the left of 0, it's going to be 0. If you're to the right of 0, it's just going to be x in that case, or x1, right? So straightforward, right? So in the end, what it means is that we can almost analytically compute all of those gradients. It's really straightforward, and that's been a revolution. And that's also why it's so much more computationally efficient to use the ReLU functions, right? Because all of those gradients, you know, if you use the sign, you know, it's kind of annoying, right? Remember, you need to get this sign, you know, in between. If you use the ReLU, it's like 0 or 1, right? So why bother, right? It's so much simpler, right? So you can compute that analytically, and in fact, that's what you have in the guts of TensorFlow and Keras and PyTorch. Everything pretty much is analytical in terms of the gradients, and that makes things way, way, way faster. Okay, in fact, that's part of the revolution. It sounds like nothing, but this chains rule is actually really, really important. Okay, so the whole process here, we call that actually backpropagation. What we mean by that is that we're trying to minimize the loss by adjusting a bunch of neurons, and we go from the end to the beginning, right? So we are going backward. We are going to backpropagate. We propagate the loss all the way to the end. Now, there's one thing that's very clear is that as we move further and further down, you know, if we have many, many, many layers, and then any of those sensitivities become 0, then there's no sensitivity at the output, right? And that's this issue of vanishing gradients that we mentioned before. And that's also why those sinusoidal functions are not ideal, because they tend to actually get to 0. So you're losing a lot of sensitivity. So it means that a lot of neurons are dead. Okay? They are not active, they are not participating, so they are pretty useless. So you typically need to expand the dimension to levels that are beyond necessary. And that's also why we typically don't use those activations functions, and we keep the ReLU, because they don't have dead or very few dead neural networks. Make sense? Okay. But that's also why you can get that pretty implicitly using this neural net, this backpropagation. Sorry. Okay. Just for fun, to show you a real activation function, again 2D. It's pretty crazy, right? And we are trying to get that guy here, right? You can get those spikes, you know, it's pretty beautiful, yeah? And just 2D again. So think of that 1 million dimensions, good luck, right? So better have a good algorithm, right? So that's why this backpropagation, you're going to love it. You know, it's going to do it the right way, okay? But the main point being that this is what we want to get. It's non-trivial because of all of those nonlinear activation functions, and that also depends on the data set that you have. Can be very complex, right? So you should not underestimate the complexity that you have in the gut of that. Okay, so quick summary, what we are trying to do, minimize some weights, okay? We do that through backpropagation, and we have this very important parameter, which is how quickly we are going to descend through that landscape, right? And so eta, which is this learning rate, is going to be very crucial. Again, we can visualize that this way. We say we are starting here. The best loss, this is just in 1D, just to make, I mean, visually we can only visualize 1D or 2D, so just to make it simple. This is the optimal value here. We want to descend here, right? So let's optimize that, right? So we're starting on the left-hand side here. That's the initial guess. And so if we have a small learning rate, it's going to be very, very slow to get there. And maybe by the end of the algorithm, we'll be just stuck here, right? If we're going too fast, again, we might be bouncing back and forth, right? So there's some sort of threshold that will be appropriate for the type of data set that we have. It's going to be data set dependent, right? It's not something, it's not a one-fit-all type of approach, right? It's going to be actually dependent on the type of data set. Okay, so that's something we need to be careful about. Okay, so now the question is, how do you find this learning rate, right? And you could say, you know what, I'm just going to try a bunch, right? So that could be okay, you know. But typically it's not so great, right? Because when you think about it, you know, if I started on the right-hand side here, I would rather want to go like really fast at first, right? I want to get to the bottom of the mountain, to the valley. And then once I'm here, you know, I want to be pretty fine-grained, right? I want to go really slowly here because I want to just really adjust to make sure I'm not getting this one, I'm not getting that one. I want to make sure I'm not getting this false one here, neither, right? So ideally, your algorithm should be what we call adaptive, right? It should actually go fast first and then go really slowly to make sure you're getting into the right minimum, right? Yeah?
Yeah, I have a comment because usually the learning rate depends on the time, right? Like
yeah.
How many steps you do, but how about, I never heard of a learning rate which depends on the loss. I don't know how to say it.
On the what, sorry?
If the learning rate depended on the loss, it would be a lot easier, right?
What do you mean the laws, sorry?
Like eta depends on the loss instead of just the time step.
So you can actually make it depend.
Slow down when you go to middle, right?
Yeah, so you can actually accumulate that, yeah. So we are going to talk about that in a minute. Okay, and that's what we are going to do. Okay, so basically in a sense, another way to say that, when it's very steep terrain, so steep loss, we know that we are computing the loss, you want to go fast. When the terrain is actually pretty flat, so meaning the loss is actually close to zero, you want to go slow. So it means actually that it's kind of funny, like the learning rate should be adaptive as a function of the loss itself, right? So typically what we do is we keep a little bit of memory of what's been going on, right? When we are going really fast for a couple of time steps, we say, well, let's continue to go fast, right? When we are starting to slow down, we say, okay, let's put the brakes, right? Let's go slowly, right? And that's what we are going to do. Okay, so we are going to do what we call adaptive learning rate, okay? That's what we are going to use today. We are going to use the ADAM adaptive learning rate, which is going to go fast at first and then slowly decrease, right? We are going to be adjusting that, right? But one thing to keep in mind is that we will always define the initial learning rate, right? How quickly we are going to descend at first, right? Then based on that, we are going to adjust, okay? But the initial one, same as the initial conditions for the weight, we are going to define that, and that's going to be the hyperparameter we are going to tweak. Okay, so we talked about that, so no need to get into that. Okay, just for reference, you have that. So those are the different types of algorithms that are kind of trying to accommodate the fact that the landscape is changing and we want to adjust the learning rate. The one we are going to use is ADAM. You know, it has kind of the good properties of each of them. It has a little bit of what we call momentum. You know, you want to carry some weight. You know, you don't want to be too fast, you know, and bouncing around. you want to also have some drag, right? As you're getting down, you want, so it's trying to get those two things, some momentum, you're keeping some memory, and some drag, right? As you get down the valley, you are actually getting some drag. Okay, so that's kind of the idea of the momentum, is that if you go too fast, you'll be bouncing around, right? And so what you want is you want to carry some momentum. You want to have some memory, of what's going on. So that's one thing you can actually include in your process. Just going to go a bit quicker here. So those are the different algorithms. So, but that's the one we are going to use, is that it has kind of all the flavors. It has this momentum approach, which is like a ball running down a slope. And it also has this idea of friction. You want to basically drag things, and you want to slow down when things are actually going slower, right? So it's this idea of friction and momentum, right? And so it prefers to have like a flat minimum in terms of the errors. Okay, so maybe that's the best way to visualize that, is that, those are different ways you can actually get down. So either with momentum, you could have those different flavors. And then you have this Adam algorithm here. And you can see some of them, they go fast really, really quickly, but they don't get, like the blue one, doesn't really get to the end very quickly, or this one here, like the red one. In the end, it stops pretty far from the optimal value, right? So what we want is we want something that goes fast first, and that will also be going close. So if you look at the yellow one, it's getting close to the truth pretty efficiently, right? Goes down quickly first, and then we'll fine-tune as we get closer and closer and closer, right? So that's the type of algorithm we will use today, right? So we are adjusting the learning rate again to go fast first, and then to basically adjust. Make sense? No need to get too much into the weeds, but I think that's just the idea that we want. Okay, so that's basically what we are going to do today, is we are going to compute those gradients. We are going to get down using this Adam algorithm here, and then we are trying to minimize that, and we are going to iterate until we stop, and that's going to be the end, okay? One thing we can do is that, so maybe let me go back just quickly to that, is that one issue could be that sometimes you can get stuck here, right? If you're going fast here, and then stop, yeah, you have a, and then you're being stuck here, so that could be an issue, right? You would want to have a little bit of likelihood to actually get up and go here, right? So if you maybe done a little bit of minimization or some programming, there's this one thing we call simulated annealing. Have you heard about that? So you're trying to minimize something like a function, but what we do, it's actually inspired by statistical mechanics, right? You give some likelihood to the molecules to actually get out of the system, right? So it's like some activation, right? Some energy, right? So it's dependent on some temperature, and depending on the kinetic energy of those molecules, they can get out, right? And that's the same idea. We want to give some likelihood to actually get out of that, because we don't want to be stuck in a local minimum, right? We want to get the best minimum that we can. And so we want to get this one here and not that one. So one thing is that if we were to use a deterministic descent, it will not work so well, right? Because we could get stuck here. And in fact, your gradient is 0, right? So locally, you have no way to say that it's a bad point, right? But if you had a mechanism by which you could get out sometimes, you could be actually lucky enough to see that this one is actually better. And you would see that this loss is actually a little bit lower than the other one. And that would be preferable, right? So one easy trick to do that, and it's actually computationally even more useful, is to say, when we compute that loss, so to get back to your earlier point, Janice, we can say, when we compute that loss, we could actually split the data. And we could say, I compute that loss not on the entire data set, but on what we call batches, And the batches, or typically we call that a mini batch, they are typically very small, size 128, 256 or something. And we compute that loss just on a subset. And what it means is that that loss will not be exactly always the same, right? It will slightly vary just by luck, because sometimes you're seeing one part of the data set, sometimes you're seeing another part of the data set. The other advantage is that you're always dealing with small chunks of data, right? 128 points tend to be very small in memory, right? So it's pretty easy to actually transform that computation of the gradient in terms of just computing over a few points as opposed to like millions of data points, right? So we typically replace that by that. We compute the gradient over what we call a batch. We will have a bunch of batches depending on how big the data set is. So if you have millions of data points, you split that into chunks of size 128 or 256. You can choose that. It's also a hyperparameter. And then you compute those gradients there, right? It will just give you a little bit of flexibility, a little bit of stochasticity, which is natural, which is just due to the data set itself, give you a little bit of a chance to actually get out, to provide some stochasticity. Plus, the advantage is you also have the benefit of chunking or cutting your data in very, very small chunks, right? Very beneficial, right? I mean, we talked about GPUs before. They are very small in memory. So you can actually do that in parallel, right? You can compute all of those weights or all of those gradients in parallel, gather the information back, and then process and move forward, right? Very, very beneficial from two standpoints. You have stochasticity plus, at the same time, small chunks of data. Perfect, right? So you tackle two things at once. Okay. Killing two birds with one stone. So that's Weiwei's paper on carbon cycle. Okay, so last thing. So basically, long story short, those mini batches are very useful. Stochasticity plus very small in memory, great. The hardware people love you. Great, you can put that on GPUs, TPUs. That's what you need. And it works better. You will get a better neural net at the same time. Now, the last thing we need to talk about is, and that's typically the one thing we want to focus on, is overfitting. Okay, that's typically the issue with neural nets. They are greedy and they want to chew on everything. Okay, they want to swallow everything. They are so strong, so powerful that they want to basically pick up everything. Okay, and we need to slow them down. We need to say, that's too much. We need to reduce the dimensionality. We need to limit overfitting. So, and the typical thing is that if you have a data set here, so again, a regression, you have a bunch of points. What a typical neural network will do, like brute force, will actually be that, fitting every single data point, right? You have millions of degrees of freedom, so why not, right? You can do it if you want, right? But it's not great, right? I mean, it's pretty obvious that if you wanted to predict, let's say you're taking another data point, say, on the right-hand side here, so I'm slightly extrapolating, I would expect that this data point would be around here, right? Now, or even in the middle, like if I have a data point, I would expect that this data point is about here, right? Now, if I had all of those wiggles, maybe my prediction will go bananas here. It will go crazy, right? And so that's going to be an issue. At the same time, if you have a very lower dimensional system, you might be underfitting, right? Think of that. You have a parabolic shape. You use a linear regression. Prediction is going to be pretty bad, right? Outside of the training sample, even within the training sample itself, right? So what we would want is something in between, right? We want to have the ideal fit. And what we mean by that is that we want to actually fit the data well, but we want to also have a good capacity to generalize well to data sets that we haven't seen, right? So that's going to be a lot of the focus, right? And pay attention today. For the competition, we are not going to be using what we call the training loss, which is on the training data set that you use, but what we will call the validation loss, right? On this data set that you've not seen. So that's going to be the one used for the competition. Okay, so to reduce that, we need a bunch of tricks, basically, and we call that typically a regularization. Okay, we need to basically slow down the neural network. We need to reduce the dimensionality as much as we can, and we need to do that in a couple of ways. Okay. The first method that we have is what we call dropout. Okay. I used to really like it. I mean, it depends on, sometimes it just doesn't work at all. But when you have a very high dimensional neural net, that tends to be pretty useful. So the idea is very simple. We have a neural net, and we discussed that before. It's very redundant, right? Remember that we are connecting every single neuron here to every single hidden layer here to every single hidden layer in the next layer, right? So it's extremely, extremely redundant, right? And we can actually get to the same answer in many, many, many different ways, right? So we want to basically avoid that, right? Straightforward ways to say, let's cut some of those links, right? They are redundant. There might be some randomness there. And so what we can do is we can, and typically it's completely arbitrary, we say we drop 50% of the links, 50% of the connections, and we just cut them, right? So we cut 50% of the connections here. And what it does is it really it's trying to reduce the dimensionality of the neural net, right? Trying to avoid a lot of the overfitting and trying to avoid a lot of the redundancy that are built into the neural network, okay? Straightforward to do in Keras. You just say, after one layer here, you say, I'm going to add a dropout layer. We call that a layer, but it's really, we are cutting the connections. And with a given probability, so in that case, 50%. We are cutting 50% of the links and 50% of the connections. Okay, so straightforward to do. We will add a layer. After that layer, we say dropout. Cut some of those connections, it's too much. And typically, again, for consistency, we don't do it in one layer and not in the other ones. We do the same across all layers. You know, just like in that picture here, we cut 50% of the links across, you know, because otherwise we don't know what we really did. You know, so that's an easier way to do it. You could look at the dimension of the neural net. At the end, it will be way smaller, right? We've reduced the dimensionality, so that's a good thing, right? It means that we were trying to basically achieve the same type of loss without overfitting too much. So that's good news, right? Typically, it works quite well, especially when you have a high-dimensional system, okay? And it's random, right? Because it's a probability, so if I do one dropout one time, I will get that. Another realization of my dropout will give me another realization, right? Sometimes it works well, sometimes it doesn't work as well. You know, it depends. You know? So there's some randomness there. Okay, so that's one strategy one could use. Okay. The other one, and that's the one we should always use, you know, this one, is what we call early stopping. And what we mean by that is that we take our data set, we split that, to get back to your earlier point, typically in terms of 80% or 20% or 70% and 30%, depending. We typically use still the bulk of the data set for training. And we use that percentage, so 70 or 80% for training those weights. Okay, we are using the data sets, we potentially use the mini batches or whatnot. And we use that to adjust the weights. Okay, so we are training and training and training. And then we have the best neural net that we have. And then we evaluate the neural network on some data set that the neural network has not seen, and we call that the validation loss, right? So we reevaluate that loss. We don't train there. You know, on that loss, we don't train again, so the weights are not changing. And we are just checking what is the mismatch that we have, okay? So it will look like that, right? As a function of time, it's actually not time, it's iteration, right? So we iterate through the weights, we are getting down the loss. That's going to be the training loss, right? It's always going down, otherwise we're making a mistake, right? If it's going up, sometimes just because of natural stochasticity, you can have some variations. You will see in the data some wiggles from time to time, but that's okay, that's normal. But on average, for over a long period of time, it goes down, right? Makes sense, we're always trying to minimize, minimize, and minimize. And then what happens is that the validation, so on the other data set that we have not seen, where we are, again, not adjusting the weights, we're just testing the values. Eventually, what will happen is it will start going up again. And so what it means is that we are trying to overfit the data. We are starting to learn the noise in the data, like to a crazy amount, right? So we are trying to say, okay, I know that data set so well, and I can reproduce the data set so well, but you have no predictive power, right? You're losing predictive power because you're learning even the noise in the data set, right? So that's a mistake. And so what you should do is you can actually include this, what we call early stopping. You can say, you know, once I see that the validation loss is not being reduced anymore, I stop, you know, and you can do that after a couple of iterations. It's a parameter like 1 to 10 or whatnot. Yeah?
Can you use both of these regularizations?
Yes, you can combine them, of course, yeah.
Validation loss is dangerous because then that just becomes overtraining.
Sorry, could you?
You only can train on the training loss, not the validation that's cheating, right?
Yeah, you're not training on the validation, yeah. You're just using that as it's a diagnostic, right? It's just a diagnostic where, and you will see when it's actually not going down anymore, you want to stop, right? One thing as well is that, and please use that for the competition, is this validation loss is also very useful to let you know whether you were overfitting or not, right? So imagine you have a very, very deep neural network. You will see very quickly that your validation loss is actually going up very quickly. So it means that your dimension, your initial dimension of the neural network was too big, right? Because your validation loss is so much bigger than the training loss, right? So if there's a big mismatch between the two, it means that your dimension is too big, right? It means you were trying to fit the data set so well, and that's a mistake, right? You're trying to fit exactly the noise in the data. And we don't want to do that, right? So if you see that there's a huge imbalance between the validation loss and the training loss, shrink the size of your data, of your neural network. Reduce the number of neurons, reduce the number of hidden layers. You were overfitting, right? Because there's too much discrepancy. Every time you're seeing a new data point, you're generalizing and you don't know what to do, right? So there's too much mismatch, okay? So always looking at this validation loss and training loss is very, very useful. That's something you should always look at. If there's too much discrepancy, again, too big of a dimension. If you're increasing too fast, you should stop early, So those are really great indicators of overfitting. It's almost the best indicator that one could use. Always visual, right? And here you will see at the bottom, so training iterations here, we typically call that epoch. Okay, that's the jargon here. What does it mean? So one epoch means you went through the entire data set once. So typically you go to like 200 epochs. You will hear people saying that, oh, I stopped after 200 epochs. So it means you went through the entire data set 200 times. Why not just once? Just because it takes time, okay? There's no magic there, but it's kind of absurd. You need to go through the same data set 200 times. But again, remember that you're taking those batches that are random, right? So they are stochastic. So you're not exactly seeing the same behavior every single time, right? There's a little bit of stochasticity in there. So that's okay, okay? We can go through the data set 200 times, okay? And that's also kind of the limit, right? Because 200 times means that this might be because of computational powers. We have a lot of luxury today, thanks to Ryan and Julius. But sometimes you need to stop, right? Because of your compute power, right? Maybe you're running that, for instance, a lot of people in my group were running that on some HPC, and we have 12 hours, right? So after 12 hours, we need to stop. So we'd better be close to the end after 12 hours, right? So that's also why you need to be careful, right? Too big a dimension could be an issue because you might not even get to the actual optimized value by the end of your allowed time, right? So that could be a concern. Yeah?
Is there any guarantees that basically that loss there doesn't reach, for example, a local minima?
Yeah, you're right. So in fact, it often does, right? And you could actually reach a local minimum here. And maybe that's something you want sometimes, So, and I don't know if that's standard practice or not. So what I do, and I think Weiwei actually does the same now, is I run not just one neural net, but I run like 5. It's just me, just because you could get good luck, bad luck, right? So I take 5, and that will really give me a good sense as to whether my hyperparameters work or not. So I take the same architecture, same number of neurons, same number of hidden layers, run the optimization 5 times, and that gives me a little bit of a sense of a sample, and I can look at the median value, what is the median loss, and I would say, on average, it behaves this way, and that would kind of avoid this, right, like just bad luck, or good luck, so removing a little bit of the just like initial condition or good luck or with a local loss, okay? So that's my trick. Tends to work quite well, especially when we want to do hyperparameter tuning. My personal experience is that those hyperparameter tuning toolboxes don't work when we only use one neural net, And so that's my trick is I run them 5 times, and that's way smoother because then it means, again, because it's that validation loss is so erratic, so doing it 5 times helps a lot, I feel. Provide some smoothing. Okay, we're almost perfect on time. Last trick, another regularization. If you've done any type of regression, we have what we call ridge and lasso regression. Who knows that? Ridge and lasso? No one? L1, L2 regularization? Yeah, so basically what you can do is you minimize your loss, and you can add one term on the right-hand side of the loss, which is plus some coefficient, which is whatever. You can tune that. It's also a hyperparameter. times either the absolute value of the weights or the squares of the weights. Why do we want to do that? Is because we don't want one weight to take over, right? We don't want just the neural network to be absurd and just going one path, right? We want the neural network to be relatively well balanced, right? That the response that we're getting is actually due to a bunch of neurons that are sharing their vote, like equal vote, right? Like basically you want your neural net to be democratic, right? And so that's what we do is we call that L1 and L2 regularizations. We just add to your loss what we call a regularization. Just again, we add some weighting of the weights, right? We want the weights to be as homogeneous as possible. And again, why do we want to do that? To make sure that one doesn't take over, okay? So that's typically very useful. Tends to provide an answer that's way smoother, so you will not get spikes. And you will see that, especially if you look at an image, typically, your image will tend to be a little bit blurry. And that makes sense because you want things to be a bit more homogeneous. If you want very sharp and abrupt contours, that will not be the right way. But if you want a regression that's very smooth, that would be the right way. Okay, so that's a good way to also avoid overfitting and spikes and things that are very contrasted. Okay, so I'm done, and I think I'm exactly on time. Great. And now we are going to get into the competition. So we are going to get into the notebooks. And that's going to be, so it's a QR code. You can scan it with your phone, hopefully, and that should lead you to a form. And then what we are going to do is we are going to basically get through a notebook during the studio together. And then I'm going to show you how we can code on your network. And you're going to adjust yourself on your network to try and get the best loss possible. So you're going to try to minimize the loss. And remember, the loss that we want is actually not this one here, which is the training loss. We want to minimize the validation loss. We will try to have a competition where people will win when the validation loss is the minimal one. Okay?
So, I'm guessing most people won't be logging into the hub from their phones.
So let's get back to, so similar to what we've done yesterday, right? So we are going to log first into GitHub. So remember Bootcamp 2023. And there's going to be one thing important is that we need to select so we have different options here in terms of the servers. We need to use the Pangeo TensorFlow ML. If you don't use that, it's not going to work. It's going to have everything loaded there, especially related to TensorFlow, which is the primary tool we are going to use for machine learning, right? So please use that. Make sure, you have different options. Make sure you take the medium one, so slightly larger RAM, so it's a CPU, and use the Pangeo TensorFlow one.
Who has a big one?
Sorry?
Who has a big one? Like a big memory? Anyone here have a big memory? Yeah.
I don't.
It was like
Depending on your status within Leap, you're going to see different things.
Yeah,
here.
okay.
Okay, but everyone in this workshop should do what's on here. Some people who are involved in Leap research may see other options on this screen.
Yeah,
it's not relevant right now, okay?
Yeah, thanks, Ryan, yeah.
So jealous.
So medium, everyone can get that? Fine? Okay, so let's run that. Should be fast. A couple of days ago, it was taking a few minutes, but we got the agreement to get that running faster, so thanks for that.
Here, if you want to show the link that will directly open
Yeah,
the lectures.
so this is this one. Please use this link at the bottom, day 2.
So if you click that, it will just directly clone the GitHub repository into the Jupyter Hub, so you can just start working immediately.
Yeah, you should have everything ready here. Can you all see that? And can you see the same files as well? Yeah, neural networks as well, you're seeing that? Okay, fine for everyone, just to make sure. Anyone struggling here or fine? Neural nets, fine? Thumbs up, we got it.
Loading, you got it.
Yeah, maybe Wei, if you could check as well with the group, be awesome.
Any trouble getting the notebooks open? It's loading. Yours, got it.
We're good, yeah? Fine? Thanks.
We're starting up. Takes a minute.
Ah, yeah, it's running, yeah? Okay. Let's wait a little, yeah.
Most people are getting it. So.
You're getting it as well? Still running for you? Okay. It's kind of slow. Usually it's fast now. You got it, yeah. Everyone got it, yeah. You got it there? Fine. Thumbs up. Here. You're solving the world already. Yeah, Bootcamp. Click on that, Bootcamp. Codes. Day 2. Neuronet. Yeah.
Okay, so that's
Got it, Oren? Yeah. You got it? Fine, fine. Oh, you're loading as well? Oh. Ah. For how long?
Did you restart the medium?
Yeah, already restarted that and choose the on. But it's still loading.
For how long has it been? A few minutes?
Yeah, a few minutes.
I think it's the same in the back. Still running for you? Still loading? Oh, it's. Oh, is this an error? Failed. So can you try again? Maybe close this one and then redo it from GitHub. Yeah. Maybe.
Here, I'll take the others.
Okay, thanks. Okay. So, Wei, there's someone also in the back there that has an issue. Thanks a lot. Okay, so let's look at what we got here. So let me make it a bit bigger for you. Is that fine because it's a bit blurry? So I hope. Yeah.
Make the text large. There you go.
Maybe like this. Should be fine. In the back, you can see. Okay. So what we are going to do is basically very similar to what we've done yesterday. X-array. We got the king of X-array here. So we got that yesterday, right? So pandas, we talked about that yesterday. So that's for data sets. And then now the only difference today is we are going to use TensorFlow, right? And we are going to use a slightly higher level API than TensorFlow, which is called Keras. Long story short, they used to be independent. Keras got absorbed within TensorFlow. TensorFlow, the original version, was a bit of a nightmare, so I went through that to run, but Keras is way simpler, okay? So Keras is basically a bunch of sequence, a bunch of lines of codes. You build your network, going to be really straightforward. You can run that. TensorFlow is more like based on a graph. It was a bit more annoying. But so Keras is going to be really easy, and that's what we have here, right? And what we are going to use is going to be what we are going to import what we call sequential. And sequential refers to basically the feed-forward neural networks that we've seen before, like the bunch of hidden layers that we have, right? It's a sequential neural net, so that's what we are going to use now, okay? We are going to, and I don't want to spend too much time here because that's not really the interest today. We went through that in details yesterday. We can download the data from the Pangeo platform. That's fantastic, right? It's amazing how easy it is, and that's basically what we are doing here. We are going to download different data sets, different scenarios. We could use different climate models output. It's beautiful. So we will be looking at some air temperature data as a function of some greenhouse gas concentration, and we can download all of that from the cloud. Beautiful. And so what we are going to do, so this is basically where we are going to pick up the data, so no need to really get into that. And we are going to be looking at what we call different scenarios. So what are those? They are, basically Julius mentioned that yesterday, they are basically what we call emission scenarios. So we are trying to predict what's going to happen in the future, and we are prescribing the concentrations of carbon dioxide, methanes, and a few important greenhouse gases, and also aerosols, if you wanted to know, in the future. And we have different scenarios here. So 1 to 6, very optimistic, wrong basically at this stage. SSP 370, slightly also optimistic, and SSP S585, which is very pessimistic. So we believe we are not on track for that. So basically, those are different range of scenarios. So low concentration, low, medium, and very high concentrations. And also on the left-hand side is what we call historical. So everything pre-2015 which is the initial date that people used to predict the scenarios, because that was run in 2015 at the time, or 2014. So they wanted to predict from 2015 on, right? So all of the scenarios, what we call SSP, so, shared socioeconomic pathways, SSPs, are going to be from 2015 on. So we have 3 of them, defining 3 different concentrations and different climate realizations, and then historical, okay? And for each of them, different groups ran different climate models. You know, we talked about that yesterday. For instance, in France, we have IPRCL. Here in the US, we have CSM, which is, they are collaborating with LEAP, it's NCAR. You have NASA also running one. So we can actually select one of the models that we want. We are just going to use one single model in that particular case, okay? And the advantage is because we have many scenarios, we can actually split the data into 2. We could have, for training here, those scenarios, and we can use a completely different scenario for testing, right? Which is nice. You know, we can have very independent data set. We rerun a full climate model with different concentrations. So that's the concentration which we call 245. We believe we're on track for that, if you're interested, which corresponds to roughly 2.6, 2.7 degrees of warming in 2100. Okay, so that's basically what is going to be our test. That's where we will want to test our model, completely independent from the training data, okay? Very straightforward, again, using the Pangeo infrastructure that we have. We are going to say we want to select a model. We want to select a bunch of scenarios. The model we select here is the Norwegian model here, NorESM. Okay, so that's just one of them. No particular choice why that's the one, but we are using that one. And what we are going to get from that model is we're going to get some CO2 concentration, some methane concentration, CH4, and we are going to try and predict surface air temperature. We could predict some other things, precipitation or whatnot, but the input predictors we are going to have are going to be CO2 and methane, and we want to predict temperature. So basically, what we are trying to do here, we are replicating a climate model. It's neat, right? I mean, you can actually get that in a fraction of seconds, right? We could actually get a climate simulation once we've trained a neural net in a fraction of seconds, right? That's great. Okay, so just to give you a sense, those are, you could actually plot those. Again, I don't want to get too much into that. Those are the different concentrations that I mentioned before. So this is the historical time series here, stopping in 2015. That's one of the scenarios, as we call it, but it's really just the past. And then we have 4 different scenarios here based on how we believe emissions are going to be. So optimistic, slightly less optimistic, 2, 4, 5. The one we are going to use for testing, this one, not the conversion. This one is for testing. This is also used for training, 370, and then 585. Okay, those are used for training. And that's for CO2, so that's basically the input of the data, and same for CH4, right? So methane. Okay, so those are the inputs here, and we are going to try and predict temperature. So Julius mentioned some of that yesterday. So how does a climate model work? We prescribe, it depends, you have different ways of doing that. You could prescribe the emission, so a flux. Very few models are actually running this way. They are getting more into that, which is a bit frustrating, if you ask me. But typically what they do is we prescribe the concentrations directly, right? So we prescribe concentrations of CO2, methane, and all of the greenhouse gases. We run the climate model with the different physics, etc., so clouds, oceans, etc. And then we predict the future of many different things: temperature, precipitation, humidity, things that were used yesterday by Julius when he was looking at the wet bulb temperature, right? He was predicting temperature and he was predicting relative humidity. But to run that, he needs to have some input, right? And that's what we call the boundary condition, right? So those conditions are basically the greenhouse gases, right? So those are going to be the input of the climate models. You run that, and then you want to predict things, okay? And we are going to use the climate model output, which is the air temperature in that particular case, and we're going to use that as our prediction, right? So that's going to be the Y that we had before, and CO2 and CH4 are going to be the X's, right? The inputs, the 2 dimension of inputs, and we are going to be predicting the temperature. Make sense? Okay, so that's what we have, okay? We can plot that as well. So this is the prediction we want to make, right? Global temperature, right? So we want to predict that temperature here. It's a time series, so that's for the historical case. and it varies depending on the CO2 concentration as well, as you would expect. The more greenhouse gases you have, the higher the temperature. Importantly, you can see that there's some variation here, right? And that's the natural variation in the climate system. You have some what we call internal variability, year-to-year variability. Actually, Ryan talked about that yesterday, such as El Nino, right? El Nino is actually creating that variability. A lot of the variability we see here is going to be El Nino, right? But we are going to use that as part of our training data, right? We are going to see different CO2 concentration, and you could think of that as the system is not deterministic, right? There's some noise, there's some stochasticity, and in a sense, it's great, you know, because the more noise and more stochasticity you have, the better it is, because you're trying to actually get, you know, this global minimum, not just like a very simple deterministic values. Okay. The other thing important is we're going to use those different lines, right? We're going to use again those 3 lines, this one, and that one, as a function of CO2, methane, and we want to predict that, right? So in a sense, on top of having this internal variability, we have 3 different realizations, so 3 different time series of CO2 and methane corresponding to time series of temperature, right? So we can use those 3, and we will use those 3 together to predict temperature. They could actually give you different answers, right? Even for the same combination, but we are going to use them together, okay? So just one thing to keep in mind. In reality, they will give you a little bit of difference, because if you look at methane here, even for the same CO2, the methane concentration is going to be different, so they will not exactly be the same. There will be a little bit of difference between those different data sets, okay? But you could have the same CO2 concentration leading to different temperatures, right? And that's also because of this adjustment in methane, and also because in your data set, there's some variability, okay? So that's okay. And you could say we might do a terrible job and we won't do a terrible job, okay? Okay, so this is the global average. So we were plotting that yesterday. Actually, that's exactly what we've done yesterday. So that's why I don't want to get back into that. We've done exactly the same thing, plotting a time series. The only change here is that we are doing that for different scenarios, but it's the exact same thing, right? So no need to get back into that. Now, the only thing is that we are now plotting that also, and we've done some of that for El Nino. We are plotting that also in space, right? Again, same thing, so then no need to get into that. And we can do it at different times, right? So I'm doing that plot using exactly the tools we've seen yesterday, plotting that in 1900, 1950, and 2000, right? We can plot those images, so it's not just a time series, but we can have that on every pixel of the globe, right? So exactly the same as what we've done yesterday for El Nino, for instance. Okay, so now comes what we want to do here today, and we can do that in the future as well. 2020, 2050, 2100, okay? And what we want to do is we want to replicate that, okay? That's going to be the objective here. We will have some carbon dioxide, some methane, and then we will try to predict maps of global air temperature. So not just a global mean, we want to predict a full map, okay? That's great, because if you're in New York, maybe the temperature is going to be different than, say, if you're in the Mediterranean or if you're in northern latitudes, right? So we want to predict basically the evolution across the globe at all times, okay? And we are going to do that. It's going to be a yearly prediction, 1 value per year, okay? We could be more granular. You could include season. We don't want to get into that, but just 1 value per year, and we are going to do that across space, okay? So we are going to predict for all of the CO2 concentrations that we have and all of the methane concentrations that we have, all of those, I don't even remember, like 2 value inputs. And then we are going to have a number of latitudes times longitudes, right, depending on the resolution of the model, times the number of time steps that we have, okay? That's what we are trying to predict. Okay, so the first thing we are going to do is that we are going to prepare the data. So no need to get too much into that, but we are going to use all of the historical data, and as I mentioned before, the 3 different scenarios, SSP 126, SSP 370, and SSP 858. And we are going to split that into a training data set and a test data set, right? And that's actually part of the utility. So if you look at this function here, this is how we are preparing the data. Really nothing super important. We are just concatenating all of those data sets because you have different scenarios. We're just stacking them together, okay? So there's really nothing super interesting here. we're just concatenating here all of that, okay, and appending all of that, right? So we just add the different data sets together. We don't care whether they are coming from different scenarios. That's not really our issue here, okay? We just stack them all. So we'll have a bunch of CO2 and methane data sets and corresponding maps at every single CO2 and methane values, different maps, right? So that's basically how we are stacking all of the data. Okay, and now that's basically going to be the core of the thing. So we could look at those things. So you could look at the training data. That's how it looks like, right? So you will have some CO2 values and you will have some methane values. Those are the ones that we have here. Okay, so again, nothing super, super important. Okay. Now, that's basically the core of the development of the neural network. So one thing we didn't mention is that typically we always want to standardize the data. So you take your input, so X, and you always want to basically make it between 0 and 1, typically, or like within roughly -1 and 1. Why? Because if you remember, we initialize some weights, right? When we start getting into the gradient descent, we have some initial weights, and we say we need to randomize them. And typically, we take them from a Gaussian distribution, you know, with mean of 0 and standard deviation of 1. So it's better if all of your data is actually normalized, okay? And the typical way of normalizing that, so it's like a z-score, you know, maybe you've seen that before. If you believe that your distribution is Gaussian, you take rid of the mean and you normalize that by the standard deviation. Another approach is you could get rid of the minimum value and normalize that by the max minus the minimum of the data set. Different flavors, doesn't matter that much, you know, but the main point being that you want your data, input data, to be roughly between -1 and 1, roughly. It doesn't need to be exact, but roughly that they are basically normalized. Why? Because, you know, it's the same thing like if you want to compare, say, some humidity as we had yesterday between 0 and 100% to a temperature that may be either in Celsius or Kelvin, they have different units, right? So that's going to be annoying. If you talk about methane, that's going to be in part per billion. If you talk about CO2, part per millions, you know, hard to compare apples and oranges, right? Better to normalize the data, looks very similar, and you can see now like your methane and CO2 concentration are going to be roughly between -1 and 1, and we are going to ingest that into the neural net. So that's much more convenient. Okay, so that's super simple. Take the mean in your data, so dot mean. We've done that yesterday as well. And you can take dot standard deviation, right? Standard deviation in your training data. And you just normalize your data. So remove the mean, divide by the standard deviation, and that's going to be your data. One important point is that I took the mean here and standard deviation in the training data. Never, never, ever do that in the validation and test set. It's called a data leakage. You've seen your validation or test set because maybe the mean has changed, right? There might have been a shift in the distribution, and you actually included that, and you think that you actually did a great job, you know? So, in fact, there's this history of people trying to predict the stock market, and they were actually doing this kind of trick. They were using the mean of the new data set and say, oh, we can predict the stock market, and that was wrong, right? So be careful about that. It's a very typical data leakage, as we call it. We use data that we should not have seen, and we are actually using that. Yeah? The Y, the shape of that is going to be latitude times longitude. Yeah. We are going to see that in a minute. And to your point, we didn't normalize the Y's, you know. And in a sense, you could say, you know, if it's only a single value, which is only air temperature, you don't need to, right? You're just predicting one thing. Remember, we have this linear activation function, and that's going to be taking care of that weighting and scaling for you. So you don't need to actually renormalize the output, but you should normalize the input. Okay, that's the important point.
Here, I got a question about this work.
Yeah.
So we're looking at it, and I'm, you know, maybe I'll sound like a broken record, but what's pandas really doing for us here? You know, we're going X-ray to pandas to NumPy to process this data.
Yeah, you could bypass that. Yeah, you could bypass that. Yeah, I agree.
We're using it for the normal.
No, yeah, for the normalization. Yeah, but you're right. Yeah, I was thinking about that yesterday. We could discard that. I was discussing that actually with Weiwei. That we don't need pandas anymore. That's a good point. next iteration, yeah. Okay, so that's basically what we have, right? That's the neural net that we have. 2 inputs here. We are going to be changing that, so that's going to be the competition. We are going to change the architecture here. And what we want to predict is basically an image. It has a shape of 96 by 144. 96 is going to be the number of latitudes times the number of longitudes, right? So it's basically an image, right? And every single neuron of the image is basically 1 pixel of the image, so the air temperature at that particular pixel for one particular CO2 and methane concentration. The time series is going to be straightforward. Those are different inputs, right? You vary CO2, you vary methane, you're going to vary the image. You're going to vary the temperature in the image in the output, okay? And we're going to use the training data, so we are going to use those pairs, right, of CO2 and methane and images coming from the climate model, and we want to replicate that, use that for the training data, and we're going to check how it does for the test set, right? We are going to discuss that later today, but what we are doing here is absurd, right? Why? Because we are treating all pixels as being independent, and they are not, of course, right? There's a lot of spatial structure in the data, and we're going to talk about convolution, but let's forget about that for now, okay? Keep that in the back of your mind. Okay, so that's what we have. So let's have fun now. So go to line 17, okay? That's what we are going to do now. We are going to start building our neural network ourselves, right? So I have a more sophisticated version here, but we are not going to start here, okay? So what we are going to do, so are you all on cell 17? Yeah? Let's forget about that for now. We are going to touch base on that in a moment. Yeah. If you don't mind, let's go simpler for now, okay? So, in fact, we are not even using those hyperparameters for now. I could even go above that, okay? So, one thing we are going to do is we are going to build a model, and the model is going to be a feed-forward neural network, right? So, in the Keras wording, remember we called that sequential. That was at the very top here. We said we are going to build a model that we're importing from Keras. It's actually a TensorFlow Keras model, which is called sequential, right? We are importing that, right? So that was here, okay? So we could have TensorFlow.Keras sequential, but we are just going to use sequential. That's the way we define that. And we are going to build that model. So as simple as it is, you just write sequential here. And what it means here is we define the model, okay? We are defining the fact that it's going to be a model where things are going to be in sequence. It's going to be a neural network, a feed-forward neural network, right? Hidden layers are going to be connected sequentially. And we are going to do one thing, right? So we are going to say we have a bunch of hidden layers, right? And we are going to start with basically a bunch of neurons, okay? So it's arbitrary for now. We could start like this. Here, let's use 64, right? We will have 64 neurons, completely arbitrary. I mean, there's nothing specific about 64. We like having powers of 2, just, you know, like it's computer world, like 32, 64, 128. But that's what we are going to do, right? So the way it works is we are going to say, we are going to do model add, dot add, right? What it means is we have our model, and we are going to add, because it's sequential, we are going to add one layer, right? And we are going to do that one at a time, okay? So one hidden layer. Okay, and that's going to be what type of layer? We are going to see there are more sophisticated layers. We're going to use a dense layer. We are connecting every single neuron ahead of us to every single neuron behind us, right? So that's a dense layer, which will have a given number of neurons. So just, again, completely arbitrary. Let's make it 64, okay? Okay. We will have a given activation function, right? I told you I like ReLU, so let's use ReLU for now. I could be proven wrong. We can use another one later. And it will have a given input shape. And the input shape, actually, that's here at the bottom. That's going to be the shape here. Is just, it's a vector of size 2. Sorry. And that's this, right? So that's the shape of the input vector, which is of size 2. So it's very simple. X train dot shape 1. So that's the first dimension here, which is of size 2. Okay, so that's what we have. Okay, so that should already be good to go. So that's the first hidden layer that we developed here. It has an activation function, which is a ReLU, taking the input layer. So we basically build up this first hidden layer, right? So we are here. Okay. One thing I like doing, just me, because I like sometimes looking at the weights, I can give it a name. Okay, like you could give it a nickname. So you could say, I can have also here name equals hidden layer 1. Okay, for instance. Okay, just me, but I like having a name because then you can get into the data set and the model and say dot hidden name. Okay. Now I'm going to add another one here. I'm going to add another layer, right? We could say I'm going to add a second layer. I want to basically replicate the schematic I have here. And so that's what I meant yesterday. So building a neural net is almost like designing, right? At this stage, it's so straightforward now that it's almost designing. We don't have to debug the gradient descent and all that. You're just designing the infrastructure and the structure. So it's very convenient. And so you do the same. I mean, nothing. Again, a dense layer. So I'm connecting all of the neurons that I had here to all of the neurons that are here, right? So that's what I should have. 64. I will do the same, right? Activation function here. A ReLU. And I will give it a different name. It will be layer 2, right? Make sense? All of you have that? Okay. So again, activation function. And I just want to, again, replicate whatever I had here. So hidden layer 3, right? So I'm going to have a third layer. Again, no particular choice, no reason for that, just for fun. To make it a bit more complicated. So I'm going to copy paste that, and I'm going to just add 3. Okay. It actually Keras learned, which is kind of convenient. It learned the right shape in between, right? It learned how many shapes there were, so you don't need to actually input that. Okay. But you need to do it first, right? Because you need to know what is going on in the first layer, and you also need to do it at the end, right? To know what is the shape then. Okay. Then so hidden layer 3, and now we are gonna basically add the last layer, right? Oh, sorry. And the last layer is gonna be again a dense layer, right? And now that's the only thing, is that now it has a different shape, right? It has the shape that we want to predict, which is the shape of the image, right? You don't need to look into that, but it's the number of longitude times latitude, which is directly given by the training data. So that's going to be y train dot shape 1, similar to what we had before. Okay. Yeah. And again, what we said is that, remember the last activation function, if it's a regression, better to make it a linear function, right? Just because you're just rescaling, the temperature can go from if it's in Kelvin, from say 250 roughly to 350, you know. So you just want to learn that. I mean, no need to actually. So activation equals linear, so that's a linear one. And I like, again, giving it a name, so that's the output layer, just my taste, you know, equals layer. And that should be good. Okay, you got that? I'm sure I made a mistake every time I'm typing on the screen or on the blackboard. I always make a mistake. So, but that should be fine, right? So very simple, we have a model. It's sequential. We added a bunch of layers, so 3 hidden layers with 64 neurons. Activation is going to be a ReLU, so nonlinear in the core, right? We gave it a bunch of names. And then we have the output, which is a shape, number of longitude times latitude. And then the activation is going to be linear, and we are going to predict the output. And now is the kind of the core of the algorithm, right? We need to say, how are we going to get those gradients? So first of all, we need to get a loss, right? We need to say what is the minimization that or what are we trying to minimize, right? So we are going to do model.compile. So that's the way we are going to compile the loss. We are going to compile the model. We are going to give it a loss. So now it's also as straightforward as that. If it were a classification, I would put cross entropy here. Here, I just need to do MSE, mean squared error. So even simpler than what I showed you even before. We used to do TF mean, reduced mean, etc. We don't need to do that anymore, right? So you could have mean squared error, or you could have mean absolute error. If you wanted to just have the absolute value as opposed to the squares, you could just do MAE. Okay, yeah?
So when you are proving that you're predicting, does the loss of one inform the other?
What do you mean?
Have to, like, let's say here you have like 138, some 10K dimensions. So does the loss of one
Yeah,
inform?
so that's a good point. So yeah, actually, that's a great point. We are predicting the loss across all of those, right? So the dimension on the right-hand side is very big, right? So we have, 13,000 points, right? Or 14,000 roughly that we are trying to predict. And the mean squared error is across all of those pixels, right? So we want to get the mean squared error across all of the pixels together. You're right. So we are going to take a batch, typically. So we'll take a bunch of those images, look at the squared error, the sum of them across the image, and take the mean of that, and we want to reduce that, okay? What is the implicit assumption we are making here? Exactly, and that's wrong, right? Completely wrong, right? We are saying that all of the pixels here are, another way to put it are IID, identically distributed, and that's wrong, right? We know it's wrong because the data is organized in space and time, right? They are sea surface temperatures. We talked about El Nino. El Nino is the proof to tell us that those things are not independent, right? If there's an El Nino, there's a very strong dependence. We talked about that yesterday, right? And that's why it's wrong, right? It's okay, that's what we typically do, but you should keep that in mind, right? There's a lot of spatial and temporal organization in the climate system. So when we do that, and when we use a mean squared error, implicitly, and you might have seen that when you were doing a regression, linear regression, mean squared error assumes that the errors are independent, right? And typically, maybe you've done that for regression. You look at the shape of the residuals, right? You want to make sure that there's no particular behavior in the residuals, right? That's a good way to check whether there's something going wrong, right? Makes sense? So that's implicit, right? Yeah.
Just one last question.
Yeah.
Forget temporal. If we are just talking about the 2D grid, and we are jointly minimizing this loss,
Right.
Is this implicitly taking care of the locality?
Yeah, the sharpness, yes. You will see that we can be pretty sharp, yeah. Yeah, you will see. Yeah, we can be surprisingly sharp, yeah. Now, to your point, like the loss here, you could actually add as part of the loss a regularization. We can actually easily add here regularization, which will try to spread out the weights. And I've done that actually exactly on those images. And what it does is it makes the field really smooth and kind of blurry, and that's not what we want in that particular case. So we are not going to do that today, but that's a good point, yeah. But you're right, we are treating all pixels the same way, and we are trying to minimize things across, and we are trying to use those weights to best predict that. Make sense? But they are all treated equal, okay? But also assumed to be independent, which is wrong. Okay, so that's the loss. We could use something else, doesn't really matter. An optimizer. Now we are going to define the optimizer. Let's say in that case that we are going to use what I mentioned before, which is Adam, right? I told you it's kind of great, most people actually use Adam, so we are going to use that, okay? We are not going to change that today. If you're curious, feel free to do that. And we are going to define here a learning rate. Okay, that's going to be the important one. So we are going to be defining the initial learning rate, right? Then there's some adaptation, right? Adaptivity of the learning rate. We are just going to define the initial learning rate, right? That's the hyperparameter that we have. So the learning rate here, let's say 0.001, just fun. And I think we're done, right? So quick summary. Again, we have a bunch of dense layers. We stack them together. We are trying to minimize a mean squared error, again, on the image. And, oh, I made a mistake. TF, yeah. And that's why I said when I'm on the board. TF.care as optimizers, we are using the Adam optimizer with a given learning rate, which is 10 to the minus 3. Why 10 to the minus 3? Why not, okay? So we are gonna use that. And we are gonna use some of that. So in the competition, you will have to change the number of neurons. You could change the activation function here. You could change the learning rate. And you could change the number of layers, okay? We are gonna discuss that in a minute, okay? So I can run that. Oh, sorry. Let me. Yeah, sorry. I need to rerun that. Okay, let me run my script. Just want to make sure. Okay. This one is not really needed. I'm going to run it anyways, and this should be, let's see. Okay, so it's as simple as that, you know. So that's kind of the advantage of using Keras. It's really just a few lines of code, you know, when you look at it. It's so simple, you know. Back in the days, people were even coding the gradient descent, you know, like the squares, you know, like the descent, you know, all of that, you know. Now it's all in the background. I made a mistake, of course. What did I do? Oh, yeah, I forgot, yeah. That's what I said, yeah. I always make a mistake. And I'm, yeah, somewhere, and I don't see that. Here, right? Here, yeah. I think I was missing this one, and here. Yeah, sorry, I was missing those brackets, and here. Yeah, after dense, there was a bracket. Sorry about that. Where is that? Here? Yes. Yeah, sorry. Oh, we'll get it. Yeah, thanks. And no, something happened. Okay, let me rerun that. Yeah, it should work. Okay. Let's wait for that. So then one thing we can do is we can look at, one thing that's very convenient is we can look at the summary of the model, okay? And what we can do is we can actually see basically the layers with the name, you know, I gave them some names, you know, like hidden layer 1, et cetera, to the output layer. Gives you the shape, so the number of neurons, et cetera. And then the advantage, and the weights here, and then the advantage is it can compute the total number of weights and biases. Okay, so that's very convenient. It gives you basically the number of degrees of freedom in your full model. And that's very convenient because you can know, like, in that case, for instance, I will have 1 million, roughly, number of parameters. So that's a lot of parameters that I need to tweak, right? So that's actually, and it tells you where they are coming from, in which layer, you know. So you could see in that particular case, it's actually in the last layer, in the output layer that I have most of them, okay?
Should we also specify the metric that we're going to optimize upon?
I don't know what's going on. And the metric I'm optimizing for is MSE, mean squared error.
For the metric.
Maybe I need to rerun the. Yeah, I think it's because it's the one from last night, actually. Let me get back to this, sorry. Oh, and I need to recode everything. Oh, no. Yeah. Oh yeah, I should still have that. And then model summary. Okay. So maybe we'll take a break. So what we are going to do next is we are going to fit the model. So far we just built the model, right? It's like designing architecture, and now we are going to fit that, and we are going to keep track of two things. Remember, we wanted to look at early stopping, of overfitting. We are going to keep track of the training loss, and we are going to keep track of the validation loss, right? And then what we are going to do is we are going to look at, so network, yeah. So you can see in the particular case we built together, so we had 3 hidden layers. We had the output layers, total number of parameters, so it explodes pretty quickly, right? 900,000 parameters. So if you're used to linear regressions, that's a lot, right? So that's why you need to have a good technique to actually find all of those weights. And remember, like, when we looked at the shape of the loss, right, we only had 2 dimensions, right? Good luck trying to get a sense of that in, with 900,000 dimensions, right? So, and most of them are actually in the last layers, right? It's the last layer that's contributing most of the weight. So remember, we are trying to predict the full image based on just 2 inputs, right? CO2 and methane, right? So that's why you have so many degrees of freedom at the end, okay? We are going to change that. We are going to play with the structure. And then the one thing we are going to do is we are going to just fit that, see how that's going to behave when we change the structure, okay? That's what we are going to do after we pray, okay? Everyone has that model summary just to make sure? Worked for everyone? Yeah? Any issues? And sorry for the brackets, yeah, and things. I'm always struggling on the board. Works for everyone? Got that? Perfect. Okay, so let's have a break and let's compete, yeah, with the neural nets, yeah. Okay. So we'll reconvene at 12:45. Okay, we have 40 minutes. Maybe some wedding music or some rock music. It depends on the mood, I guess.
Are you calling me so late?
Is everyone back? So I'm just gonna refill my coffee. Sorry, I didn't. Okay. So let's get back to business. So we're deviating a little bit from the original plan. So we are spending a little bit more time now in the studio as opposed to the lecture. I don't think you will complain. And then we'll get a little bit later into, like in 30 minutes, we'll get into the convolutional neural net. You know, that's going to be relatively straightforward. Okay, so what were we doing before lunch? We basically built a very simple architecture here. Again, fit for a neural network, a bunch of hidden layers. We have 3 of them. We have the output here, learning rate, Adam optimizer, and we are minimizing the loss, okay? Again, at this stage, we haven't done anything, no training, anything. It's just the architecture, right? We looked at the summary, just diagnostic. I mean, we are not doing anything here, just a diagnostic to get a sense as to what is the dimension that we have here, 900,000 degrees of freedom, so it's a lot. But that's potentially what we will need, okay? One thing I wanted to, got a nice question during the break, you know. Remember here, those are different pixels, right? And remember those are latitude and longitude, and depending on how we actually basically convert that to a vector, you might have all of the lower latitudes at this, like, kind of stacked together, right? So for instance, all of the lower latitudes will be here. But it doesn't matter, right? You could have a high latitude point close to a lower latitude plot, right? You could have the Amazon here close to the poles, right? It doesn't matter at all. And in fact, it will not change the quality of the prediction, right? There's no sense of organization here. So that's something to keep in mind. There's really no sense of spatial structure here. We could shuffle all of those pixels across. Doesn't matter, as long as, of course, as we are keeping the same structure when we are training. but it doesn't matter where those pixels are, right? We can replicate that anywhere, okay? That's actually very important. Remember, and that's related to the point we made earlier, that we assume that those pixels are independent, right? We are training them independently, right? Or, like yesterday, for instance, we talked about El Nino. We could actually take just a subset of the image. That would be actually kind of fun. We could predict just El Nino. Maybe we will do a better job by just restricting ourselves to a region, right? That's something we could do, you know, if we wanted to just predict El Nino potentially. Okay. So again, no sense of organization here. All pixels are independent. Okay, so now that's going to be the core of the training. So we are going to do two things. We are going to, remember we wanted to limit overfitting. So we are going to do this early stopping thing, right? So we are going to do chars.callbacks.early stopping. So we are monitoring the loss. You know, we are going to plot that, don't worry. And we are going to say we are going to do early stopping on something, and the something is going to be the validation loss. We could choose any of those, right? We could, where was my, I think I closed that. Sorry, let me just go back to, where was that? Yeah, here, okay. If you remember here, we had training iteration, validation loss, and for the early stopping, we don't really care so much about the training loss, right? We want to care about the validation loss. So that's why we are saying, look at the validation loss for the early stopping, right? That's what we want to do, right? So, but we need to specify that. I mean, TensorFlow or Keras doesn't know that a priori. Where are we? So, yeah, Firefox is here. Okay. And an important parameter here is, and I got the question before, we are going to use what we call patience. Okay, patience is just a parameter. Simple name makes sense. We are waiting for a few epochs, so we are going through the whole data set couple of times, in that case 20 times, because it could happen that you could have a little bit of spikes, you know, in the loss. So your validation loss, you know, the plot that I had was very, very smooth. In reality, it's not like that, right? You could have spikes. So we just say, let's wait for 20 iterations. And after those 20 iterations, if we see no improvement whatsoever, we're going to stop, but at the initial point, right? Before those 20 patience epochs, right? So we are just going to wait for 20 time steps, basically. And then, as simple as that, we are going to train the model, right? So in TensorFlow, it's called train. Here in TensorFlow, it's called fit. And we are just going to train those neural networks, right? And remember, what we are doing here is feeding the weights. We have some input data, some labeled data, so it's supervised learning, a regression problem, and we are trying to actually feed that, right? So the input is going to be some data set that we call X-train, right? The one we prepared above with the different scenarios. Y-train, that's the prediction, right? So those are the labeled images of temperature at different CO2 and methane concentrations. We can change, and we talked about that before, the size of the mini batch. Okay, we had that question earlier, right? So 32, 64, 128, that's a hyperparameter that one can tune. Let's use that. So here I had selected 64, doesn't really matter for that purpose. And for how long we are going to run, right? We need to be reasonable here, right? We have some limited compute power. If you're doing that on the cloud and you're paying for that, you know, better want to be careful. So you're going to be specifying a number of epochs. So in that case, the maximum number of epochs we are going to run the model for is going to be 50. Okay, it's not super complicated, so 50 should be roughly reasonable, but that's when we are going to stop, right? We don't want to go forever. And potentially, the early stopping will stop even earlier, right? So earlier than the 50, you know, if we have anything that's working well. Okay, and that's it, right? And then the only thing is that typically when we do this training and validation, we need to split the data, as I mentioned earlier. So we take the whole data set, and we say we'll split that into one part that we are going to use to tune the weights, and the other one that we are using to validate the model, right? And on that validation data set, we are never retuning the weights, right? We are just using that to evaluate the loss, but we don't have the step where we retune the weights, right? So the tuning of the weights is just in the validation set and not in the training, just in the training set, sorry, oh, I apologize. We are just training the weights in the training set, and we are using the validation just as a diagnostic, right? So no tuning whatsoever, okay? In that case, we say 20% of the data is going to be used for validation. So that's the 0.2, 20%. Okay. So let's use that. So if you could try that, you just need to click here, run that cell, and that's starting. Okay, so we are training. So what are we doing? We are actually doing backpropagation with Adam strategy, right? Starting with the given learning rate that we had learned, we had selected before. We are doing that on batches, like small batches, so it's stochastic, right? Mini batches of a given site, which was 64. And we are looking at that across different epochs. So one epoch is, again, we are going through the entire data set once, twice, et cetera, et cetera. What should happen is that the loss, which is here the training loss, should be going down, right? Remember the curve we had seen before? It should be going down. And we have the validation loss here, right? So that's also one thing that should also go down. Okay, so we could track that. Okay, so that's still, I think that's stopped. Okay, so that's great. It stopped after 25 epochs. I don't know in your case, that could be random. Anyone got a different number than 25? Try and run it, please, yeah, just to make sure.
Maybe it has the same seed, I don't know.
I don't think so.
Okay, now it's only 24. Maybe it's
24, okay, great. 27, okay, so no, not the same seed, so that's right.
The less the better.
Make sense? Works for everyone? Success? Thumbs up? Okay, great. So you actually train your first neural network, or maybe some people have done that before. Okay, so one thing we want to pay attention to is, let's look at the loss here, right? So the number is going down, and you can see here, right, the number 135.96, we are plateauing, right? So makes sense that, you know, we would want typically to stop, and you could actually look even here, the number we went from 127 to 128, 75, and 126, okay? So in fact, if you look at the number at the top, we had 0.27 already, and we are kind of wiggling around, right? We are very, very close to 127 all the time. So it means there's really no improvement whatsoever, okay? So we should stop, and that's the early stopping that we had before, and that's why we are stopping at 25, right? There was no improvement. The validation loss is telling us, like, no, please wait. We are trying to fit the noise in the data. We are overdoing it, so let's stop now. Okay. And we can visualize that. That might be even better. And you can see that's the training loss and the validation loss. They happen to be, I mean, typically the training loss is below. I mean, no need to get too much into that. But the main point being that the validation loss is actually going up here, and it's pretty flat, right? So that we would want to stop, right? There's no need to continue, right? But you can see that the training loss, you could actually zoom in, is actually getting down a little, right? So we are starting to overfit, right? And we would want to actually avoid the overfitting. Typically, we want to stop around here, right? So that's why we had this early stopping. Make sense to everyone? So as you see, it's surprisingly simple, right? I mean, it's just a few lines of code. We really harvested two things, right? We could get the climate data from Pangeo, you know, straight, you know, so it was really just a few lines of code to actually get some pretty complex climate data at the annual time scale, different scenarios, etc. And we leveraged the fact that this architecture, especially Keras, is really, really simple. Like adding a few layers works well, okay? So that's fine. You can save the model, doesn't really matter. I like doing that because if you want to reuse that. And now we can evaluate the model on something else. So the one test here is that we would want to actually test the model on the other scenario we have not used. Remember, we took off one of the scenarios. So that was SSP 245. And we want to test the model on the scenario. So we are, again, no need to actually get too much into that. But we are loading the model that we just had. So that's a way to save your model. You can save it somewhere and load it later. So that's, you save the model here. We call it nn_model.h5 somewhere, and then you're loading that later. You could load that because you want to pass it over to someone else. I have this great model, let me give it to you. You have a publication, great. Put that model somewhere, you know, and just give the link to someone. They can load the model, replicate your data, so it's very, very useful, right? And what the model is actually very simple. It's a bunch of weights, right? Just a bunch of weights and biases, so it's just a matrix, right? So it's really, or tensor, so really, really simple. Okay, and then we can do the same, right? We can, so I don't know where I was here. Yeah, so we can test that on some other data set here, so SSP 2.4, and we are going to plot that. Okay, so no need to get too much into the weeds, but we are using exactly what we've been using yesterday with Ryan, right? Just the plotting exercise. Okay, so let's look at that. On the right-hand side was this SSP 245. So that's a climate model here. And that's the prediction we just made with our neural net, right? Pretty good, right? And you can see it's actually quite nice. I mean, you can see the continents quite well, like Australia, South America, North America, you know, Africa, great. And you can also see a lot of the gradients that we see in terms of latitudes as well, right? So quite nice, right? So that's in 2030. Why 2030? So it's 2030, but remember, it's actually not really a year that we have as an input. It's actually the corresponding CO2 and methane concentration for that particular year in that particular scenario. That's how it's defined, okay? We use year here, but that's year within that scenario, just so for you to know, okay? And then we can do that 2050 here. So see, that's again doing quite well. Remember, we never saw that particular scenario, right? We never saw those particular concentration and methane in our training data, or not that particular climate realization, but we are doing a great job, right? And we can go all the way to 2100. Notice that we capture even all of the structure here, you know, at the northern latitude, so what we call the Arctic amplification, the fact that it's much warmer at the northern latitudes than the rest, okay? In fact, we're going to expand. Right, so, and that's going to be, yeah, exactly. So if you could run that, you know, everyone is going to be getting something slightly different, right? Yeah. And that's okay, yeah?
It seems like it does potentially better at 2100 than 2030 for things like ENSO or the Southern Ocean.
Right. Yeah, and that's basically signal to noise ratio, right? We are going to see that in a minute. So here, the signal we are trying to predict is climate change, right? And so we expect that to be very, very strong by 2100, right, by definition, especially when you are in a high greenhouse gas concentration scenario, right? So for that particular scenario, you're right, but you could even be going further, and you could say, I could also look across scenarios. And in the low emission scenarios, I do expect to be doing a poorer job than in the higher scenarios. You're right, right? It's just signal to noise ratio, right? We can go one step further and say, you know what? A neural network, let's remember that it's a deterministic component, right? So the machinery is deterministic. So this map, if I were to regenerate another one for the same CO2 and methane, will be exactly the same one, right? Now, if I'm rerunning a climate model, we slightly perturb the climate model, so every climate model is going to be slightly different, and that's what Julius yesterday referred to as the ensemble members, right? There's going to be slight variations between different models that are just inherent to the climate system, right? We have some internal variability. There are some internal stochasticity in the climate system. So we cannot be perfectly replicating that. We're going to see that in a minute. And that's also why we might be missing some modes of variability, right? So for instance, you should not expect to get an El Nino with that model, right? Because that's not something that can be explained directly by as a yearly value as a function of CO2 and methane, right? So we should not have an El Nino. If you have one, that's a mistake, okay? There's an issue. Does that make sense, right? We are not capturing internal variability, right? So in another way to say that is that if we look back at the time series that we have, remember that we had a lot of variability here. That was the internal stochasticity in the climate system, right? Internal variability such as El Nino and so on and so forth. We are not capturing that. The neural network is trying to do a smoothing of all of that, right? It's trying to fit a deterministic line, a deterministic curve through all of them. Makes sense? Yeah?
The plots are not a function of the year, right?
Yeah, that's what I meant, that we say year, but it's really, for each year here, especially in the future, you will have different CO2 concentration depending on the type of emissions you assume.
So what do we use to do those predictions? Like, are those estimated CO, like?
They are based on CO2 and methane, yeah. So basically, you need to have what we call an integrated assessment model. So you need to have a coupled system so you can actually define for a given amount of emissions that people put in. You need to know how much the land is going to take up, how much the ocean is going to take up, and then you need to make basically it's a mass balance to tell you how much CO2 and methane you will have in the atmosphere. And that's what we use as forcing for those climate models. So we don't directly use years. They never see year anywhere, but they see CO2 and methane as input. You know, it's just for the plotting here because most people have no sense about like CO2. If I were to plot CO2 on that plot, no one will know what I mean, but years, you do know years, right? But that's, yeah, just to give a sense of that. Does that make sense? Any questions, yeah?
So just looking at the visuals, that's making me think about other types of models, like a random forest-based prediction would maybe look floppier. That's one advantage of using like convolutional networks, is there's smoother visual outputs. But I'm curious from the science of this work, what's the inductive bias of convolutional networks that take in that neighborhood context? You know, why is that advantageous for these types of models?
That's a great point. So let me maybe go back to this. I would say, you're right. I could actually use your favorite regression tree, random forest, or gradient boosting, or whatnot, right? In fact, for that, I would say, doesn't matter. As just give me the best model, right? And you can test that. Sometimes it's unclear which one is going to be giving you the best result. Typically, what happens is that when you have a lot of data, the neural nets tend to be superior. They tend to be doing a better job, but you need a lot more data. When your data set is a bit small, XGBoost, random forest, etc., tends to be doing a better job. You know, just kind of very simply. Now, what we are going to cover later is that it's true in this case because we assumed again that every pixel was independent basically from the neighbor in terms of how we compute the loss. So you're right, you could actually use a regression tree. But what we are going to do next is actually capturing or using the spatial features. And for that, you cannot do that with a random forest or an XG or gradient boosting, right? So that will be a huge advantage of neural networks is embedding those autocorrelation in space and time, okay? And that's something we cannot do with regression trees. Does that make sense? So I would say you're right at this stage, you know, you could actually use a random forest, fine. And yeah.
So the X test is like, it's 82 CO2 and methane pairs throughout time, but those are just slices. If you make like a random, like increasing and decreasing CO2 level, and you run that and predict, it's not going to predict correctly?
It's going to predict correctly. Because we also assume when we do that is that, and that's actually a great question, is that we assume that every year is actually independent. You know, we are not using any type of, so we assume that pixels were independent in space, but we also assume that years were also independent in time, right? So I'm using CO2, methane, assuming I can predict temperature right now, just based on that. I don't need any memory in the climate system as part of that. So what it means is that I can shuffle the years, right? And in fact, we are doing that within the mini batch strategy. We are shuffling the images that we are getting, but you don't see that, right? But we are shuffling them, yeah. If we wanted to include a memory, and we are going to do that at the end, you cannot shuffle randomly because you're going to break some of those autocorrelations in time, right? So that's going to be a slightly more subtle aspect. Similar to the spatial autocorrelation, right? In that case, we cannot just shuffle the pixels, right? We need to preserve the spatial context as well. Does that make sense?
Yeah, I guess in my head it's like if you have a different type of emission scenario, like if we drop to net zero immediately,
Yeah.
the temperature is going to sustain high, which could be like
In real life, but the model cannot do that. The model cannot do that because it only sees, yeah, and that's completely right. I mean,
but the climate model could. With
the climate model could, yeah, exactly. If you had a ramp or if you had a sharp decrease in CO2, or if you could assume, actually, we played that game with an intern back this summer. We used actually machine learning for that. But anyways, you can drop emissions, but you're right. I mean, you could have some memory, like the ocean, for instance, you know. But this model could not capture that, right? Because we are saying that I would take a high CO2, and that will be similar to having a low CO2 when the temperature was lower, but I know that my temperature will be higher for quite some time, right? We cannot capture that here. What you could do, though, is you could say, I could include a memory process so that my temperature now is actually dependent on the past temperature as well. You could think of that, basically what we are trying to do, it's a dynamical system, right? So in that case, that could make sense. You could say, I could look at the change in CO2, and I could see how my system is behaving. Yeah, that's a good point. Yeah. Does that answer you all? Yeah. But that's a great point. And that's also why, I mean, to me, that's exactly why physical intuition should always be like the winning component here, right? Brute forcing machine learning is wrong, right? I mean, when people say, okay, I can do whatever, no, that's not true. You can do whatever on the training data that you have, but you're right, that's exactly one example where it was not working because you were doing something that you had not seen in your training data, right? So in that case, it would be the wrong thing to do, to say, I'm gonna predict what's going to happen. That's wrong, you're gonna get the wrong prediction, okay? Another example that to me is very useful is population and CO2. Highly correlated, right? So why don't I actually put population density or population here on the left-hand side and predict the temperature? Because population is going to be flattening out, right, and plateauing, but CO2 will keep on going up, right? So that's a time when there will be a decorrelation between the two. If I were to use population, it would be the wrong thing to do in the future, right? So that's a case, again, where correlation and causation or physical drivers are really important. Always try to use physical intuition when building those tools, okay? Yeah?
Oh, it was just a comment based on what you just said. I mean, it's kind of like a Bayesian school of thought, as Professor Andrew Gemmon would say. I mean, you have to know something about the prior to get a good posterior, right? If you have a bad prior, then you won't make good predictions.
Yeah, that's true.
It's kind of like you already know something you're going to predict. It's a bit circular. I mean,
yeah, exactly. I mean, prior, or we talked about inductive bias. I mean, that's the same thing. In that case, we are using our physical prior, right? Our physical inductive bias, right? I mean, to me, I love this one. So I will never give it away. Okay, good. Any questions so far? Everyone managed to run that? Fine. Did you get your maps? Are they very similar to mine? Everyone should have a slightly different map, you know. Okay, you got that? Looks good. And again, we are not capturing everything exactly the same, but that's okay. You know, again, there might be some internal variability we're not capturing.
are the truths the same?
Oh yeah, the truth should be the same, yeah, of course. Otherwise, it's wrong class or wrong bootcamp. Okay, so let's have fun now. So if you can run that, if you know where you were born. So actually, I put Paris here. So what you can do is now let's look at some time series, right? So we have pixels here, and now we can look at those time series and compare that to the climate model, right? And we can do that in the past, and we can do that in the future. Okay, so for fun here, cell 23, we started by doing oh, sorry, I forgot that. We are starting by putting the latitude and longitude of New York. And you can actually now plot the time series the same way we've done that yesterday, dot cell, right? Remember we've done that yesterday? So we can actually plot that, and we can compare the truth to the prediction, right? So that's going to be what we are going to do. So just run that. Okay, so that's, again, slightly different from what I had before because I have a slightly different neural net. So the truth here, please run that. So that's just here in New York, from 2015 on, what's going to be the prediction here in terms of warming compared to pre-industrial. First of all, note that we are already above 1, right, degree, so that's what you should expect. And then in that particular scenario, we are going to about 3.5, right, which is higher than what I told you before. The global average is 2.6 because we're over land, so it tends to warm up a little bit more, as we are on the coast, so it's not, sometimes it can be double, but roughly, right? So it's more than 2.6. And the main point here is that this is the climate model, okay, the blue. Importantly, and that goes back to your point, you have some variability, right? And that's the natural variability in the system, right? So you could look at longer time scales if you wanted to drop, say, the emissions, but this is the natural variability, sometimes a couple of years, right? So you have some modes of variability that are important, some at the yearly time scale, some at the sub-seasonal time scale, some at the multi-year time scales. But that generates some variability here that we are not capturing in the neural net. Okay, that's very important. The neural net is actually deterministic. It only depends on CO2, right? And in that case, and methane, sorry, thanks. And so we made it increasing because CO2 and methane are increasing as a function of time. There's no decrease in that particular scenario. It could be actually decreasing in that case if we had a reduction. But what we are showing is that it's really smooth, right? So, and that you would expect. It's a deterministic model, right? If it were really erratic, it would mean there's some sign of overfitting. Something is not right, right? There's something going on. It's kind of smooth, so the behavior seems nice. That sounds like a pretty reasonable model. Fits the data very well, so seems to work quite well. So just for fun, you can change that to your particular, so wherever you were born. So I just put that to Paris. You can look up on Google Map, change that, and try where you were born, and you can plot that. And that will be the result of the climate model, and you can compare that to the neural net. So please do that just for fun, just to try.
I was born in the North Pole.
Sorry?
It's really bad.
You mean we're a bit biased? Slightly biased potentially at that pixel, but remember, because we are using the model that was fitting the entire globe, right? It doesn't mean that we are not biased at a particular point. Yeah, you're right. Yeah, that's a very good point. Yeah, we can be biased at some particular location. Okay, so please try and enter. So I just put like Paris just for fun, so we can try it again. And that's how it looks like. So maybe less biased, to your point, at that particular location. So it's going to be warming less, so maybe better place to retire, so just for me. I'll keep that in my mind. So try it just to see if it works.
Down, like in Greenland, south of Greenland or something. That's a good place to be.
Yeah, maybe good. Yeah, Canada, maybe. Yeah, Montreal, maybe a better place. Yeah, but that's a global average. Yeah, don't forget about winter. Right? Yeah. Does it work for everyone? And you should all be getting kind of a similar curve, which is a very smooth curve for the neural net as opposed to the climate model. I think that's the main take home here, is that we have this very smooth behavior. Make sense? Good? Okay, so we got that. We managed to provide maps, and we have some nice time series, so we managed to basically do everything we almost wanted to do with the neural net, okay? Now, we're going to revisit that and be slightly more flexible than what we had before, okay? So we are going to go back to the structure of the neural net. So remember, we started here. So I was just replicating the structure I had above. So I had as a structure this guy here. And what we are going to do is we are going to make it slightly more flexible. So we entered here a model that's slightly more flexible, right? And that's the one you're going to tune now for the competition. So we are going to have a model. So it's the same, right? Nothing super complicated, but it's the same. It's a model that has a first input layer and then a bunch of hidden layers. So we call that n_layers. So that's the one hyperparameter you will tune. And we're going to stack a bunch of layers that have a shape of n number of neurons with a given activation function, right? Value, okay? And then we use the same Keras optimizer, so we can actually use that. Okay, we can actually use this guy. We can summarize that, make sure it works, and then we can actually train that as well. Okay, should work similarly. Okay, so for instance, in that case, I didn't go over I had to go to more epochs, right? Okay, and I can compare the loss. Can plot that as well. Okay, so see, slightly more erratic here, but tends to work quite well. I don't remember. Yeah, I'm slightly higher than what I had before, validation loss. Okay, so what we are going to do now is we are going to report. So we are going to get back to the competition here. So I put like a Pong video game at the top. Please enter your email here. You can have a nickname like arcade game. You can choose whatever you prefer. Yeah, okay, so now we know it does. And those are the hyperparameters you are going to use, right? Number of hidden layers here. Number of neurons per hidden layer. We are going to use the same across, right? That's going to be too complicated otherwise. Activation function. I let you choose. I gave you another choice here. Where is that here? You can change that. So remember, the activation is going to be here. You can change that. And to change that, you will need to look at the hyperparameters here. So you can actually comment that now. We don't need that anymore. So the things you're going to change is this, number of neurons. Activation here. I gave you another one that I would suggest, which is this leaky ReLU. What is leaky ReLU? It's the same as rectified linear unit, except to the left of 0, you have a slight slope with a given slope, right, of 0.2. So it's almost like this one-to-one line, except we make it with a slope of 0.2, right? Why? Because we don't want to get stuck on the left-hand side, right? Because otherwise, remember, the gradient is 0 on the left-hand side, and we don't want that, right? So people typically use that. Very strong, abrupt gradient to the right, and weak gradient to the left. Okay, you can use that. And then the learning rate, right? Very important, the learning rate. How quickly are we going to descend? That's the initial learning rate, and then we use Adam, right? So those are the ones you can change. So the learning rate here. And please don't touch the other ones, right? Number of epochs, mini batch size, we are not going to touch today. If you're interested, you can change just to make sure we have time, okay? So activation function, sorry. Number of epochs we can change, sorry, we changed that. Activation function you can change, report whatever is working best for you. Learning rate you can change, and then number of epochs. So for instance, 50 was a bit potentially small in that particular case, especially as you get deeper and deeper, you might want to get and add more. And then report your last training loss and your last validation loss, okay? And we'll try and compete so that we get the best validation loss across the group to get a sense, okay? And we'll get a sense also of the diversity we can get across the group, okay? So I will give you, let's say, 20 minutes, okay? Should be fine to do the best you can do in terms of changing those. And the link should be, should be in Slack, okay? If you don't have the link, please let me know.
So we're gonna fix the number of hidden layers.
Yeah. So you can, sorry, let me repeat. So you're free to change the number of hidden layers, change the number of neurons, change the activation function, change the learning rate, and the number of epochs in that particular Jupyter hub, so here. And do that multiple times. Write somewhere, maybe in an Excel file, what is your best set, what is your best solution, and only report the best solution that you have at the end, in 20 minutes. Don't report all of them, just the best solution, okay? But try a bunch of them. So I don't know a priori what is the answer. If you work really big, it will fit quite well the training loss, maybe not so the validation loss, right? Because you will be overfitting. If it's too small, the converse, right? You will not be training so well, okay? Number of epochs can work nicely, but we are limited in terms of time, right? Same as compute power. So you might want to be small, right? Or not too big, because otherwise you're wasting your time for the competition, right? And then the activation loss, you don't have too much flexibility, so just 2, I would say. Does that answer? Okay. Any questions? People are getting stressed already.
What we care about is validation loss.
What we care about is validation loss. The competition will be on validation loss, yeah. Typical climate data are organized in space. So we talked about convolutions, right? So one way to actually account for spatial structure, especially over long spatial ranges as well. And there's, of course, the obvious thing, and we talked about that before. I mean, you had this great comment about the fact that there's memory in the climate system, right? And that's something we would want to pick up. In everything we've been doing when we had the neural nets, we had the convolutions, we're using snapshots, right? So we could actually shuffle in time, right? That was no problem, right? We could use future time, past time, different CO2, different scenarios. We brought all of that together, right? What we'd like to do now is saying, you know, there might be some memory, right, in the climate system. So how can we actually include that, right? So we won't get too much into the weeds, you know, but just to give you a sense that there are ways to actually do that. We call that using recurrence, using a recurrent neural network. And what we want to do here is actually using some temporal features, right? We want to say that basically there's some autoregressive autocorrelation in the time series that we have. And we want to use that, using that temporal context to refine the prediction that we are making. If you've been dealing with the dynamical systems, we want to basically define some sort of ODE, right? Ordinary differential equations, right? We want to say dx dt equals stuff, right? That's really what we're after here. Okay, so where is that coming from? From a couple of things. So some of the earlier exploitation of that started in natural language processing, right? So phones are great now, or if you go to Google Translate, for instance, you can translate sentences or even like paragraphs or even chapters really, really efficiently, right? So a lot of that started from those developments of recurrent neural networks, right? DNAs and genes, you know, so those are also pretty long sequences, you know, so it's a sequence, right? So that's what we are looking at here. Every time you have a sequence, so things come and are actually being ordered in time or in some sort of sequence, that's when you will typically want to use one of those recurrent neural network, right? So time series, words, or even or letters in a word, words in a paragraph, paragraphs in a document, etc., right? Or frames in a video. People have been using that. Actually, we have colleagues here trying to do next frame prediction. It's kind of fun, you know, you have a car, you know, driving, you know, like actually one of the member of LEAP, Carl Van Drik, like looking at cars and you want to predict what's going to happen next. You know, it's kind of fun. You're trying to predict the future, right? So how can you do that, right? You want to have some temporal context, right? It cannot just be random. Okay, so there's actually a lot of implications here. And that's actually very similar to what we had discussed before. When you have pixels, right, they are spatially organized, right? So there's actually some spatial covariation, right? In time, it means that there's some autocorrelation, right? So one time point is going to be dependent on the previous time point, and potentially there's also a relationship with the next time step, right? And really what it means is that data points in time are not, again, independent, identically distributed. So basically, if you want to look at the next time step, you cannot just say it's random, right? And you shuffle from some randomized distribution. It's going to be highly dependent on the previous time step, okay? That makes a lot of sense. Same goes, again, the example of the stock market, right? People use what they call martingales, right? So the best prediction of the future is right now, right? So you know that there's some dependence on now, right? I mean, that's at least one way to think about that, okay? And that's really one thing we want to account for, right? We want to say that we don't want to assume that things are independent in time. We want to say there's going to be this autocorrelation, so how can I use that to my advantage, right? So to have a model that's actually not trying to overfit too much, right? So similar as sentences here, right? So you could have structure in a sequence here, like I know that you know, et cetera, and you want to actually extract some pieces here. And we want to use that on short time steps, but potentially also on longer time steps, right? If you think, for instance, of a typical time series, you could have a lot of variations at the daily time scale. We talked about seasonal time scales yesterday. You could have El Nino as well, right? So you could have multiple time scales that could be important, right? So you could have short-term but also long-term type of memories, right? Typically, you would want to capture those, right? So that's going to be one thing we'll be focusing on. So, so that's maybe linear regression not 101, 102, let's say. Second class is when you have a time series, the equivalent of a linear regression is what we call an autoregressive model. Who has seen that? Who has not seen that before? Raise your hand if you've never seen an autoregressive model. Don't feel shy. Fine, so maybe a few of you. So basically the idea, pretty simple, is that we want to predict a time series point, so y of t, and that's going to be same as what we've seen before, right? A bias here, plus some regression, so some weights, times the previous time step, plus 2 steps ahead, right? Et cetera, et cetera. You can take as many time steps as you want. We call that an autoregressive model of order p. Order p means we stop at p time steps ahead of us, right? So if you've done any dynamical system, if it's order 1, it's a first order differential equation, order 2, second order differential equation, et cetera, et cetera. So how many orders do you have in your equation, okay? It's the simplest model you could have. It's basically a linear regression, and you hope that the residuals here are going to be IID in that case, and there's going to be no structure here, and the only structure in time is coming from the dependence on the previous time steps of the process itself, okay? So that's the simplest you could have. And remember what we've seen for neural networks, it was actually not too different from a linear regression, right? It was kind of like a regression, except that we added an activation function, right? A nonlinear one. So we should be inspired by that, looking at this model and say, in fact, we would want to take that and just add some activation function, right? It's almost the same, right? I mean, that's always what we do with a neural network. You take something that's people have done, say, in statistics, add some activation function, and you get a miracle, right? That's basically what you do. Okay. Second approach you could do is you could say, that would be kind of the flip side of that. You could say, you know what? I can predict the next time step as a function of a bunch of time steps, and I can do it in a nonlinear fashion. I know how to do that. I can use a neural net, right? So I can just connect every single time step ahead to the time step later, right? So that would be okay, right? You could do it directly here, so you could have a bunch of weights, right? Fine. Or you could be more subtle. So typically, people have what they call hidden layers, right? So you could say, I can do some sort of manipulation in between. I have what we call a hidden state, you know. If you've done Markovian type of models, so you can have this hidden state, you know, that can do things in between, right? And so think of that, for instance, you want to predict, say, evaporation. You could take as input precipitation over a couple of days. And then you have, as a hidden variable, you have soil moisture, right? So that's how much regulation you have of evaporation by soil moisture. So that's a hidden variable that you don't directly observe, but something that's going to be modifying evaporation, right? So that would be your hidden variable, right? So that would be another option here. Can make things with a latent space or not. You can make things nonlinear, but that's kind of, those are kind of the two perspectives, right? A linear approach, kind of nicely framed as an autoregressive model, and then the other one is directly encoding, and again, similar to the feed-forward neural net, we are connecting everything to everything, right? We are totally overdoing the job here, right? And so that's kind of similar. You could have dynamical systems, right? You can write equations, right? dx dt equals stuff, right? And you can solve that. And you could have what we call hidden Markov models. So that's what I mentioned before. You could have some driving variables here. You can have a hidden state, and you can have outputs here, and you can do it in a probabilistic setup as well. What's nice is you can carry memory across in the hidden state. So that's the idea of the Markov state, is you're carrying memory across the hidden state. So for instance, you're feeding precipitation here. You want to predict evaporation. And the hidden state is going to be soil moisture. So the memory is coming in. And basically, you're adding the input here, but all of the memory is kind of in the middle here, right? So the idea of the recurrent neural network is that we want to combine all of those things together, right? We want to say we want things to be nonlinear. We ideally, oh, I don't know what's going on. Sorry. It's a bit tight here. So we want to combine those things. So a hidden state, because that's kind of nice. We can do some manipulation, and we don't need to basically keep track of all of the input data, right? That can be annoying. You don't want to preserve all of the precipitation data from the last month to predict sun moisture now, right? You just want to have some sort of carryover effect. And we want things to be stochastic, right? That would be ideal as well, not deterministic neither, right? So we want to have this flavor, and we want to do the same as the autoregressive model. We want the residuals to be typically IID and not the process itself, right? The process has some memory as a function of the different time steps. So we are trying to combine all of those different flavors together, right? And that's the idea of recurrent neural network. Okay, so it's going to be very similar to what we've done before. So we are going to have a bunch of inputs here. We are going to predict the outputs here. The only change compared to what we had before is we are going to have a bunch of hidden layers here that are going to carry memory forward in time. So what this means is that before that, when we just look across, like in the column here, that's similar to what we had, right? Input to output, right? That's a neural network, right? Feed forward, that's fine. The only change is this arrow here, right? We're going from time step 1 to time step 2, time step 3, et cetera, et cetera. And what we are doing here is that we have a bunch of neural networks here, a bunch of neurons here. They are taking as input, of course, the input here, but also the previous memory that they had in the hidden state, okay? So what it means is that now in the hidden layer, we are capturing the input plus the past time step. Okay, so that's the new thing, right? We are adding the past memory, the past time step. And we can do that over and over again, right? We can go to the next time step. So you can think of that, those are different days. So we got some precipitation that day, gonna feed that into the hidden state. That day we didn't get any precipitation, so no precip here, but we feed field 0 here. It doesn't mean that it becomes 0 because we got some memory of some moisture or some precipitation from the previous day, right? And then we're going to predict something such as evaporation, right? And then we keep on moving further, further and further in time, right? So that's day 1, 2, 3, 4, 5, always the input from at a given time, and we carry forward the memory here. Make sense? So the only change that we really got here is that we added some memory here by adding those arrows here, okay? We are taking the time steps and we are saying one current time step is dependent on the previous time step, right? And if it's dependent on the previous time step, you could say it's also dependent on the next time step or the previous time, 2 steps ahead, 3, 4, et cetera, et cetera, et cetera. So you could think of that it's dependent on an infinite number of time steps, right? Because you can go, you know, further back in time as much as you want, right? Okay? So how do you then train that, right? So that's the question, right? So that's the recurrent neural network. So you're going to pass that over, right? Same as the perceptron here. We have a bunch of hidden layers, a bunch of neurons. Feed that into a bunch of hidden layers, typically 1 here. And then that hidden layer at that particular time step is going to be feeding that into the future as well, okay? And now what do we need to do, right? We have a bunch of data. So we will have some labeled data at the top. The labeled data is going to be a time series. Could be multivariate, doesn't matter. We have a bunch of input data here as well, multivariate as well. And we are going to try and feed that, right? So that's going to be the process here. And you can think of that as kind of a black box here where we have some input data here. You have the memory there, and you're trying to predict the output at a given time. Okay, and you pass that through some nonlinear functions such as a hyperbolic tangent or ReLU or whatever you want. Okay, so one way to think about that, so people like writing it this way. That's why they call it recurrent neural network, because this time is going into the next time, so it's like rolling that, you know. So we could sometimes call that unrolling the neural net, right? Because the one time step is going to feed that into the feed itself into the next time step, because it's the same structure, right? We preserve the same structure. Those are the same weights, right, that you provide further and further back in time, right? So we just have the same weights, so it's the same structure over and over again. The only thing that's changing here is the input here, and because that input state is changing, that's going to change also that, right, because of the memory and whatever you saw in the past, okay? So basically, it's as simple as that, right? And then what do we need to do? Train that, right? So you define a loss. Output here typically means squared error. You would want to do a regression, and you need to fit a bunch of weights here and a bunch of weights here, right? And they are the same, right? So they repeat themselves. Okay? What's the issue? That's going to be the main issue here. Those who know, please don't. Yeah? Gradients, yeah, and why? Yes, they will tend to explode. So the issue is that everything depends on everything, right? Because we have a time series, right? We want to minimize the gradient, so I will start looking at, okay, what's the influence of my weight here on this output here? Pretty obvious, that's fine. Influence of the previous time step on this one, that's fine, I can look at the weights, but now we have some weights here, but the same weights are coming here, right? And they are coming here as well, right? So if you remember your linear algebra, right, you have basically a matrix multiplication, right? And you will have, if it were to be linear, those will be eigenvalues, right? And the eigenvalues, you know, depending on the coefficient, can either explode or shrink to 0, right? So when you multiply those matrices over and over again, they either shrink to 0 or they explode, okay? And so it doesn't work, okay? So practically, those don't work, okay? So even though in principle they are great, they actually don't work, right? So that's basically the issue, is that the backpropagation, which we wouldn't want to do, we are trying to do the exact same backpropagation, but eventually the backpropagation will go further and further and further in time and will either explode or vanish. So it's very, very difficult in practice to actually vanish. So you could use some tricks. You could say, I restrict myself to just a few time steps, you know. But typically, especially if you have, say, a seasonal cycle or you have a sentence, I mean, you want to have like pretty long time steps, right? Pretty long sequences, right? So they don't really work so well, okay? So they are pretty much impractical, okay? So basically, they explode, okay? And the main point is because you multiply the same matrix again and again, and that will lead to vanishing and exploding gradients. Okay, so how do we get around that? So that was a trick that people used. They said, in fact, we are overdoing the job, right? We are trying to use all of the information all the time. So the trick here was to say, we're going to use some of the information sometimes, okay? So we will have what we will call forget gates. We will use some of the input sometimes. We will use some of the past sometimes, but not all the time, okay? And that's going to be, we will just have gates, 0, 1s, binaries, right? And again, we can train all of that. And that will actually tell you whether you should write and read, like if it's an input, or if you should even reset the entire state, right? So it's like, you could think of that, that's really very much inspired by transistors and things like that, okay? So you will have what we'll call input, output, and forget gates. So into the structure that we had before, we are going to add a bunch of those gates. So we will actually allow to actually use or not the input, use or not the memory, and either discard the same for the output. So we will have those just gates, okay? So one way to frame that is just to frame it this way, okay? You have the input here. You have an input gate that will tell you whether you're using that or not. For the memory, same thing. Are you using the memory or not to make the prediction, right? And there might be times when you don't need that, right? So, for instance, a good example is you want to look at runoff, right? You have some precipitation data, and maybe you have some memory in soil moisture. But if it rains so bad, you know, it's going to, run off eventually, right? So maybe you want to forget about the state about soil moisture, and you want to focus on that, right? So you're just trying to put some focus on different things, right? And that's basically the idea, is that forget gate is going to be helping you focus on things that are important for that particular time step. Okay? And the same goes for the output as well, right, as you would expect. Okay, so that's basically this idea, and we call that LSTM, long short-term memory, and that's a practical way to make recurrent neural network work. So it's basically the same as a recurrent neural net, but with gates. Yeah?
It's again the same structure in every
it's the same structure, except that it's within the structure itself. So it's within the one that we're replicating. We have those gates within those replicating structures as well.
So the forget happens the same
Yes.
always.
Not, yeah, that's a good point. The forget happens sometimes. So at some, so you have a sequence, right? So maybe at time 2, you're not going to use the input. Maybe at time 5, and depending on the state, right, you're not going to use the input. You know, so that's actually state varying, which is the important thing. It's depending on the state. Okay, and that's a way to avoid those exploding gradients, because eventually you're not using all of those matrix multiplications, so you keep the focus in a sense. But you're replicating the same structure. So the structure is again the same, right? It's always the same for those neural networks because we want to train them. So the structure has to remain the same, right? And it's just that they are going to be state dependent, right? So sometimes we're going to use them, sometimes we're not. Okay, so that's kind of the idea. You have this gating that modulates information. So either we are either using that or not, and it's just a sigmoid function, right? So it's really like similar to what we had for synapses before, 0, 1, right? I mean, you are using the information or not, so it's a range in between. And then sometimes you're forgetting as well, you know, the previous state, you know, so that you can actually really encode the information from the past or not, right? So how much of the information are you using? And so in the end, it makes it a much more practical way of actually using this information. And the advantage being that in that case, you can actually use memory that's actually much longer in time because you don't have those exploding gradients. So if you have a very long sentence, you can actually use that. If you have a very long time series, you can actually use that pretty efficiently. Okay, so they tend to work quite well. They are pretty practical, and they can be trained much better than a typical recurrent neural network. Maybe one thing is that very typically they don't have a ReLU function. They tend to have a hyperbolic tangent, just to get into the weeds here, but that because they were basically developed typically a little bit before the revolution in neural networks. Yeah, so how does it look like? So this is the typical recurrent neural network, right? So we pass the information across, and that's going to be the LSTM, right? So sometimes you're actually blocking, so sometimes you can actually block or not. So when there's an O, that's the standard notation. I'm not a big fan of that because it sounds as if it were blocked, but it means that the flow of information is passing through, and here it's blocked, right? The gate is being blocked. And here the information, so it means that this output is going to be mostly dependent on the input here, right? And here you're using all of the information across, so that prediction is going to be using mostly the memory, not the input here, and same for this one, right? So for precipitation, that would be, again, a good example. Sometimes it rains, sometimes it doesn't, so why would you want to use that information across, right? And you're only using that whenever it matters, right? But sometimes you want to carry memory forward, right? And then that's how you're going to make the prediction. Okay? And that makes it much more efficient. You can see that basically you're cutting the recurrence in chunks, right? So it makes it much more tailored to actually to the memory process itself. Okay? So that's what people use in practice. This LSTM, long short-term memory, LSTM is really the practical way of doing recurrence. And I put actually the slide in. I don't know why it ended up here. There's one thing you need to know is that this is one way to do it forward, but there's also a way to do it bidirectional, right? You can use the past to predict the future, but you could also use future to predict the past. So we call that a bidirectional recurrence, right? There's no reason why. I mean, it depends. So if you want to do a forecast, yes, you would want to do an LSTM, but sometimes you want to do the best type of product using the past and the future. So you could think of that. This is similar to your weather forecast, right? You have observations in the past, want to predict the future. This is similar if you're familiar with that with reanalysis, right? A reanalysis product, you use future and past to get your best estimate. Those are exactly the same. And you can show that this one is always going to be better than this one, right? Because you have a hidden state carrying the information forward, and then you have another hidden state here carrying the information backward, right? So by definition, this one you can show will always be better if trained correctly, right? Because you're using information from the future to inform the past as well. Make sense? Okay. Any questions? Yeah?
So you can't use the bidirectional if you're trying to predict the future and you only have the past data, right?
If you have the future and you want to predict the past, so you could actually use LSTM backward, you know, so there's no need to actually use this one, right? If you want to predict, so I think it depends on the task, you know, if you want to predict the best estimate of something in the past and you have access to data before and after, you know, you should use that bidirectional, right? If you want to do a prediction ahead of time, so weather, streamflow data in the future, then you should use that, right? Because you will not have access to the future, right? But it depends on the type of problems you could have, you know. If it's pure language translation, for instance, you have the future and the past, right? So you can actually use that, right? Nothing, I mean, there's no, but while you're typing, you know, you don't know the future yet, right? So when you're typing, you know, autocompletion should use that, right? So it depends on the type of problems you're looking at. Any questions? We have a little bit of time. We can have another 15-minute break, so we are on time for Studio 3, and then we'll go quickly. It's not that long, and then we can have a break. We can have a drink, and maybe we'll have some data points to make sure we're progressing.
So we'll do a survey at the very end. Are we ready for that now?
Actually, we are done, yeah. So then we'll get quickly into the Studio 3 just through the notebook, so we can do that at the end, if that's okay.
And then we'll switch
Perfect.
to the survey, and then we'll break.
Yeah, and if people have any questions, you want to learn more about climate data, etc., happy to take questions. Okay, let's have a little break then. So we are reconvening in 15 minutes.